Good morning, everyone, and welcome to Hedera DevDay. We'll be getting started in 10 minutes. Please find a seat and settle in. Good morning, everyone, and welcome to Hedera DevDay. We'll be getting started here in about 5 minutes. Please find your way to the main stage as we are about to get started very soon.
se ve eso, te ves como travieso, quiero probar tu beso. Ay, qué rico se ve eso, te ves como travieso, quiero probar tu beso.
Hedera DevDay is about to begin. Please take your seats, settle in, and get ready to spend the day building with us. Please join me in welcoming to the stage our MC for the day, Hashgraph's Head of Developer Relations, Ed Marquez.
Good morning, everyone. Good morning, everyone. Awesome. Welcome to Hedera DevDay. I'm Ed Marquez. I lead the developer relations team for Hedera at Hashgraph, and I'll be your MC for the day. Now, for those of you who are not too familiar with Hashgraph, you can think of us as the labs function and more for the Hedera network and the Hedera ecosystem. Now, for those who are here, we really want to thank you for coming and spending your time with us today. We know there's a lot happening all around Denver, and today's all about you. We want you to get the most value out of this event. We want you to move at your own pace, and there's really no right way to do Dev Day. So the goal is simple, and it is for you to leave here feeling excited, connected, and informed about everything that is happening on Hedera and what you can build next. Now, at a high level, here's how the day is going to flow. We're going to start shortly here with the technical content, and you're going to see a mix of talks, workshops, and hands-on sessions. And you're going to hear from folks like Richard Bair, our VP of Engineering, the one and only Dr. Leemon Baird. You're also going to hear from Hashgraph engineers, Hedera teams, ecosystem teams, and builders, all who are deep into the industry and the network. Now, a big part of the day lives outside of the main stage, right? It also lives in the Devs Day stations, and those are the interactive hubs that you see spread out throughout the venue today. Those are focused on different use cases, tools, and different themes. So they're also designed to be quick, approachable, and you can build something relatively quick without having to commit to a long session. Now, as you complete those stations, as you check out these talks today, you can also compete in the scavenger hunt. And so that's a really fun and interactive challenge or series of challenges where you're going to be collecting rewards and points. So you'll be competing for up to $3,000 in prizes. That's just a fun incentive for you to get connected and get to know people along the way. But in fact, there's a lot more happening this week, right? Today we have the scavenger hunt here. There's also a capture the flag, which is going to be a Hedera-specific set of challenges that are focused on security, and they're meant to help you learn best practices for building safer and more robust applications. And the prize pool for that is $6,000, and that goes until Friday at midnight. So be sure to check out the CTF station so you can learn more about how you can participate and how you can get started. You also have the ETHDenver hackathon. That's where you are going to have the chance to build and compete for a $25,000 prize pool, and that includes a $10,000 bounty for OpenClaw, for building a killer app for the agentic society. So very much looking forward to what you all build for that. There's also going to be challenges for smart contracts that execute themselves. You're going to see a workshop on that. Also a bounty for building with the native SDKs and much more. That's not all. Today, just a couple of hours ago, we announced the Hedera Hello Future Hackathon, the Apex chapter. And that is a global virtual hackathon where you're going to be able to compete for $250,000 in prizes. There you can build towards AI, DeFi, tokenization, ESG, and so much more. And there you're going to get support from an amazing team of mentors, Hedera experts, the ecosystem, community, and so much more. So that goes until March 23rd, so you have over a month to prepare and build and join for that experience. Now, in terms of housekeeping for the day, the meals, the snacks, the breaks, all of that is scheduled already for you. That's part of the program. The venue has different signs that will point you to the right places. Also, the bathrooms, the quiet areas, they're clearly marked. And then if you have any questions, you feel lost, need any help, just grab someone, feel free to ask. We're here to help. There's plenty of people from Hashgraph, plenty of people from the ecosystem who want to make this a great experience. Also, as a reminder, we're streaming this to YouTube. So if you have friends or your network couldn't be here, please share this with them so that they can join us if they couldn't be here in person. All right, so the last thing is, if at any time you also have any questions, want to say hi, or need any help, feel free to grab me. Looking forward to making this a great experience. And thank you all again for being here. Let's have a great Hedera DevDay. All right, to kick things off with the technical content, this first session takes a look at where Hedera is today and where it's headed next. This session is going to cover the most compelling and significant engineering milestones from the last year, from protocol upgrades to developer experience focus to developer tooling, and also taking a look at what's powering enterprise and production-grade applications at scale on Hedera. Please join me in welcoming Richard Bair.
All right, good morning, everybody. Glad you could come out, and I hope that this will be useful for you. I'm going to talk about actually less of what we've done and more of what we're planning on doing this year, and more of the way that we see the work that we're going to do this year. What are the things that are most important to us? And then I'm going to talk about some of the big projects that maybe we haven't really talked about so much publicly that we're really working on. So the first is that there are three key focus areas that we are looking to address this year. The first one is developer experience. Now, our sort of North Star on this is delighting developers, giving developers the best experience when running on Hedera. And this includes developers who are using our Hedera APIs and developers who are writing smart contracts and deploying those smart contracts to our network. We've made a lot of progress over the years in terms of improving that developer experience, and we're putting a lot more work into that this year, which I'll talk a little bit more about. The second one is in EVM smart contracts, or in other words, on-chain programmability. The ability to have your business logic running on-chain in addition to just off-chain and then sending commands to the network, and making that a high-performance experience and a really effective experience. That's another area that we're focusing on. And then the third area is around scalability and performance, which is my personal love. It's the thing that I really enjoy, is making things really scale and get the performance really high. And so that's one of our other main goal areas, is to really take our scalability and performance to the next level. So let's begin by talking a little bit about developer experience. One of the projects that we started last year and that we've been working on throughout the year, we continue to work on this year, is a project called Solo. Now, one of the challenges in our system for developers is if you want to set up a network and you want to do testing, it's very difficult to do. And generally you will use testnet. And the problem is when lots of people use testnet, you run into throttle limitations and all sorts of other problems. You also want to have a certain amount of state that's available to you, or maybe you want to test your application in high performance, or maybe on larger number of nodes, a lot of different scenarios you might want to test your application on. Solo is the ideal way to do that. We use Solo extensively internally for all of our performance work and for all the build and verifications that we do for every build before it goes into Hedera mainnet. we use Solo. And Solo allows you to basically, if you have a Kubernetes environment, it'll deploy all the containers that are the same code that we use in mainnet. It'll deploy mirror nodes, block nodes, consensus nodes, JSON RPC relays, proxies, all the different things that make up the system. And then you're able to run your tests against it. Now, currently, Solo takes too much memory, and it takes too long to start. And those are things that we're focusing on right now to make it so that it's truly trivial for you to just spin up a network and execute your tests against it. We have a mode that's called one-shot mode, so you can do a Solo one-shot, and it'll just create a simple network for you, single node network. But you can also configure it to run as many nodes as you like. Another thing that we've been working on this year on the developer experience side is fees. One of the things that's nice in Ethereum is that if you have an application and you want to know, within a reasonable percentage how much it's going to cost you to execute, you can sort of pre-run that transaction on a node, and it'll tell you, oh, this is how much gas that you used, and you can kind of figure out what the price is. It's been more difficult for us to figure out exactly what the price of our different fees are, especially programmatically. You didn't really have a good way to do that. This HIP 1261, improves this. It makes it so that you can go to a mirror node or just from the SDK itself and give it a transaction. It'll be able to give you a very accurate price for what that transaction is going to cost. Previously, all we had was the web UI that you go into, and you could sort of configure all the different settings, and then it'll tell you what the price is. And since we have fixed predictable fees, that was very useful, but it's a lot of manual work. So we're automating all of that so that you can actually price things out ahead of time. So that one's coming. It's very close to landing on mainnet. A third category of things that we're working on, of course, is AI and how you can use AI. We have various MCP servers. We've moved our Docs platform to Mintlify that gives better integration for AIs to make use of. And we've also recently integrated the X402 payment standard on Hedera so that you can make use of that. Hedera is extremely well situated for the world of AI. The low fixed predictable fees is a big deal. Low latency is a big deal. And as agents get the ability to sort of choose the most effective network, I think that we're going to be in a good situation. And we definitely want Hedera to be the place that an agent wants to be because of the speed and the cost and the other things that are important to them. So those are three areas that we're working on for developer experience. There's many more. We're working on SDK improvements and many other things to try to improve that developer experience. And we're very open to the feedback. In fact, that's one of the most crucial things that we can get help from is just what do we need to do to improve the developer experience. All right, now I'm going to talk about the on-chain programmability. To me, this is a very important thing. The ability to put your logic on chain is empowering and important. Now, we started off in this journey in the simple way, which was, you just take a basic EVM application and you can deploy it and it works. If you want to deploy an ERC20 smart contract, you can do so, or an ERC 721, you can do so. Everything works. We use a fully compliant EVM, and that's all good. But what we really want is the ability to take that to another level. So the first thing, when we first released our enhanced smart contract platform, we were 10x Ethereum. We were able to do 15 million gas per second. But what we found was that there was a sort of an artificial limitation that was being introduced due to the way that we were doing the throttling. We've fixed that in what we call our ops throttles. And in our ops throttling, we throttle it different than we used to. When we try with a real AMM on the network, we're able to get over 150 million gas per second, which is 10x what we had been doing just a few months ago. So this really unlocks the amount of stuff that you can execute on chain. There's also a new feature that we're adding, which is called hooks. And hooks allow you to add that on-chain logic or programmability to existing Hedera APIs. So for example, if you wanted to transfer some token from entity to entity, you could put a hook on your entity that says, when somebody tries to transfer this token to me, let me decide whether I want to accept it or not from them. And these are essentially just little places that you can put smart contract logic and then you can have sort of arbitrary logic implemented in there. And the hooks, of course, are done in a very carefully from a security perspective. And initially, our first hooks that we're putting out will be hooks for sort of authentic authorizations and approvals. Today, if you want to do an authorization and approval, the way that it works is you say, okay, that smart contract wants to be able to take money from this account or take some tokens from this account. In order to do that, the account pre-approves that contract. But it's just a very blunt instrument. It's the same way that it's done on Ethereum, which is to say, I approve them and I approve them for this allowance. And then you have to sort of manage that allowance over time. With hooks doing this for you, you can have much more complex logic. You could say, I will approve it as long as it's at this rate. They can have this much per day, or any sort of arbitrary logic that you want to put in there. So it really gives a lot more control over how those Hedera APIs work by giving you the ability to write code and deploy it without having to wait for us to add a whole pile of new features. And we really sort of unlock the capabilities of the network. And then the third area where we have a strong focus this year is around compatibility. We've done a lot of work previously in order to make our system more compatible, supporting tools like Hardhat and Forge. But there are some challenges because our model is different from Ethereum's model in terms of consensus. For Ethereum, it's a leader-based consensus mechanism, and when the leader builds a block, they decide what transactions go into that block, and if any transaction can't execute, they can just leave it out of the block and put whatever they want in it. For us, we have a total fair, no front-running, no MEV, democratic process in our consensus system that selects which transactions to execute, which means when that transaction gets executed, we may find at execution time that the transaction cannot execute, and so how we deal with nonces and everything else has to be a little bit different than the way that it's done on Ethereum. But that introduces friction for developers who are coming from Ethereum to Hedera. So we're putting a lot of effort in how can we innovate around making the relay handle more of this complexity for the user so that you can deploy your own relay and you can send your transactions to it, and it will maintain what we call the mempool. It's like an Ethereum mempool, except it's not shared across multiple relays. It's just that one relay. Basically, it has a buffer of all your transactions, and it will just make sure that it plays them in the right order, that they succeed before it places the next one, so that it can manage the nonces properly for you, and just really increase compatibility and reduce toil for developers who are going to deploy their stuff to the EVM. All right, the third area that I'm going to talk about is scalability and performance. So the first one is increasing world state. If you're familiar with the concept of world state, it's all the state that's currently held by the network. Not the historical state, but the current understanding of all the state in the world. What is the current account balance? What are the current state of each smart contract? And we have dramatically grown our world state over the years, and we are striving for and very close to supporting billions of accounts and tokens and other entities. In fact, we already do. The challenge is to be able to do that at high TPS loads. The sort of tests that we run, just to give you an idea, it'd be very easy for us to write a test that said, let's have a couple billion entities in state, and then let's just do some crypto transfers across a few of them. And you can get tremendously high throughput, no problem. And in fact, you could have almost infinite state that way, no problem. When we run our tests, in such a way that we are doing a stochastic probability across the entire set of all of the accounts. So it's more or less a random distribution, if you will, in which we are touching many different accounts in that state. And boy, does that put a lot of load on disks. And so the bigger you get the state, the more complicated it is to do hashing and all the other things that are going into it. There's some really hard engineering that's going into this area to try to get us to that point where even just on a single shard, we'll be able to handle billions of accounts with the 10K plus TPS. Speaking of which, 10K plus TPS won't be the limit forever, folks. Our internal tests are much higher, and we're striving to be able to bring that to you. I'll talk about that in a second. Okay, and then the other one is reducing latency. Today, our end-to-end latency on mainnet is somewhere in the 5 to 7 second range. The time it takes to get to consensus is around 2 to 3 seconds. So end-to-end latency is the time from when you submit a transaction to when it goes through the entire system and you can see the result in the mirror node. So the complete the complete passing of all of those pieces. And we are on track to be able to reduce that latency to under 3 seconds this year. Now, the block nodes that we talked about last year at this conference are a part of that. They help us to reduce that latency. But also we're doing a lot of work on the consensus nodes themselves in order to tune them to reduce that latency. So those are kind of the main things that we are focused on and working on this year. Now I want to transition into some crazy things that we're working on this year. And just to be clear, these are moonshots. There's no promise of success. In fact, you're probably, if you even get 50%, you're probably doing well. So I'm not making any promises for what we're doing. But for each one of these things, we have a realistic expectation that they're possible, and we're working very hard on these. So I want to share these with you. The first one is called Project Bonneville. This one is a moonshot that was born out of an internal hackathon that we did last year. And the idea was, can we build a gigagas EVM? For those who don't know, that means over 1 billion gas per second. Can you create an EVM that'll be able to run at over 1 billion gas per second? And you do it by implementing a just-in-time compiler. What a just-in-time compiler would do is it'll take your EVM bytecodes or opcodes, and it will transform them into raw machine code execution. So today, all of our EVMs, as far as I'm aware, all of them in the world are interpreters. They're all interpreters. They take the EVM opcodes, and then they execute those opcodes. But what we want to do is we want to convert from that sort of interpreter model to being able to actually JIT the resulting bytecodes and get native performance. In other words, an EVM program should run at the same speed that a corresponding native program would execute. It should be on the same order of magnitude. And our goal is not just to be as fast as other EVMs, but to be the fastest EVM on Earth. And we think that this is achievable. Again, no promises. Maybe JIT just doesn't work with EVM. We'll find out. But this is a project that we are actively underway and working on. Another project that I'm really excited about goes to the topic of latency. And this project is called Lightspeed. The question can be asked, what's the fundamental latency limitation? You'll see chains that have 500 milliseconds or 700 milliseconds sort of claimed as their latencies. And the challenge in getting latency is all around the communication time between the nodes. And if you are a democratic consensus algorithm like ours, then it's really any network, to be honest with you. Every network that exists, at some point, since it's a decentralized distributed network, at some point your transaction has to be gossiped to everybody else in the network. That has to happen. Either as part of the transaction being gossiped and then included into a block, or in terms of your transaction was sent to a node, which then included it a block and gossiped the block to everybody. One way or another, everybody is limited by the transmission time from node to node. The only way to get really small latencies is to try to minimize the amount of overhead in that process. And in our case, when we look at the worldwide latency of the network, we need to have greater than 2/3 of our nodes. As soon as they come to consensus, the transaction comes to consensus. So your transaction has to find its way to at least just greater than 2/3 of all the nodes in the network, and then it can be brought to consensus and life is good. When you look at a globally distributed network, your best ping time, or say your worst ping times are around 300 milliseconds. Your best ping times might be around 70 or 50, depending on which nodes you have. So overall, if you were to just ballpark it, you might say around 250 milliseconds for those ping times. Now, the Hashgraph algorithm, what makes it so good at performance and at latency in particular is that it adds no additional network traffic. It's just the time it takes to spread your transaction out is the bulk of the latency. From there, every node is executing everything locally. It's running the voting algorithm, the Hashgraph voting algorithm locally. It executes the state locally. It creates blocks locally. It exports those blocks to a block node. But it doesn't wait until the entire block is done to give it to the block node. We're actually streaming the block results as it's being computed. And then the block node is receiving that, doing its own verification, and streaming it out even before the block proof comes, streaming it out to mirror nodes, which then are able to prepare it to get ingested into the database. And then as soon as the block proof completes on the consensus node, it's sent to the block node, which is then sent to the mirror node, and you have your proof. It gets committed in the database, and you have your data. All of that together introduces very little latency over top the initial gossip. So we believe that it should be possible to bring the latency of the network down to the theoretical minimums, which are based on the speed of light, which is why we call this Project Lightspeed. We really are trying to bring it down to those theoretical minimums. And of course, speed of light in a cable, which is maybe 80% of C. But that's what we're trying to do with the Project Lightspeed. All right, another moonshot that we are working on, we call it Project Full Send. This one really is speculative. Don't pin your hopes on this one. I'm just telling you, but I want you to be aware of what we're working on, what we're trying to do, and we're looking for brilliant ideas if people have them. What we want to do is we want to be able to remove the artificial throttles. You've heard about this a lot over the years. The reason that we have the throttles is because we need some way to limit the input of transactions into the network so that the network doesn't have a glut of transactions that then slows everything down and fills up memory. So there has to be some sort of a gate at the front end. And today, the way that we do this is that we test exhaustively to make sure that the throttles that we set are conservative enough that every transaction will be able to handle the load. And this has worked very well for us. We've been able to sleep very well at night, knowing that even when we run at 10K TPS, we know that that's not our limit. We know that it's a conservative throttle, and so therefore we don't have to worry about it. But wouldn't it be great if you were able to run the network at the full throughput that it's capable of doing? If every node was keeping track of its own health and its own load and sharing that information with all the other nodes in the network, and they were able to deterministically conclude what the throttles should be, so that the throttles would truly be based on the types of transactions that we're handling and the quantity of those transactions we're handling, so that we could continue to protect the network, but we could go well above that 10K TPS number that we have today. This is a difficult problem. Not like on the surface, it's relatively straightforward. It's like, in the concept that I just gave you, you could look at it and say, yeah, that should work. We're going to keep track of health information to share it with everybody else. What makes it challenging is working through all the adversarial scenarios of how one node could lie to another node, and how do you make sure that it's correct, that nobody can sort of unduly affect the throttle of the system, and so forth. So that's what makes it a more challenging project. But it's something that we are working on. And again, if I were to say any of these that we're talking about today, the likelihood that this one is completed this year, I'd put it at a very low probability. I think that some of the other ones I talked about, much higher probability. This one, it's a very low probability. But it is something that we're working on. And it's something that we would love to be able to complete. And so I wanted to be able to share that with you today. Now, I do have one more moonshot that I want to talk about. And this is another one of those interesting problems. And it's about bridging between networks. Today, there are a handful of bridges that we support on Hedera, layer 0 being one of them. And all of the bridging approaches that have been designed so far require some third network. There's basically your source ledger, then there's some kind of a validator ledger network that the bridge operates, and then there's your destination network. And this always bothered Leemon, and he didn't think that that was the best way to design one of these things. And he thought, wouldn't it be great if you could just eliminate that middle set of nodes that you have to trust? Because now you're trusting 3 different entities. What if we could get it down to 2? What if we could just have the source ledger communicate directly with the destination ledger and vice versa to move any type of value? And we've been working on this idea for a few months. And the name of this project is CLPR. We've been calling it Clipper. It's a working name. We might come up with a different name for it. But it just stands for the Cross Ledger Protocol. This cross-ledger protocol has an interesting characteristic, which, if you're familiar with Hashgraph, shouldn't be surprising. It's ABFT, asynchronous Byzantine fault tolerant, the highest level of security that you can get in a distributed system. If the two networks are ABFT, it also is ABFT. You'll have ABFT across the entire system. So if you were looking at, say, Hedera mainnet and, say, a Hyro network that you're setting up as like a hash sphere or something like this, you could have an ABFT bridge between both sides. It's also incredibly fast. There are no bridge nodes, and there's no need for any type of liquidity pools. And it was truly designed to be 100% decentralized. And by that I mean there's not an authority. Anybody could take the Clipper contract, deploy it to a network, set up your own configuration on it, and be able to start bridging between two networks. And that's really appealing. There's no DAO, there's no entity that you have to go to and say, please list my token. You can just list your token. There's nothing that stops you from being able to do that, and that enables the flow of liquidity to and from Hedera. So this moonshot, we call it bridgeless bridging, in that there's not a bridge network. It's just the two sides directly talking to each other. It works great for Hedera and Hashspheres or other Hyro networks that you set up, because, like I said, if it's ABFT on both sides, the whole thing is ABFT, which means that you're never going to lose your value, even if there's network disruption or other things like that. The other thing that's interesting about this is, I mentioned, if you have if you do sort of a traditional ledger, there's sort of some set of validation nodes in the middle that have to sort of agree to something before it can be finalized on the destination. But with Clipper, this isn't the case. You're trusting the two networks themselves. The source network is saying, these are my messages, and here is a state proof that proves it. And it's the source ledger that does that. And the destination ledger then just needs to be able to verify the state proof coming from the source ledger, and then it knows that this is legitimate and it can do the processing. Then it can create responses and sign it as a network with a state proof. And then that goes back to the source, who then knows that these things were accurate. You're not trusting any individual nodes. You're simply trusting the networks on both sides. Now, I mentioned the speed, the low latency. It really comes down to the speed of consensus on the two sides. So if you have two networks that have longer latencies, the overall latency will be higher. And if you have two networks that have very low latencies, like, say, Project Lightspeed level latencies, you're going to get those cross-ledger transfers in under a second. It's going to be very fast. So there's a real opportunity to have a bridge that is really fast between networks that have really low latencies. And then the last point is also one of the essential design points of Clipper is that it needs to be able to work with any arbitrary network without having to convince those networks to build it into their core protocol. So I mentioned that there will be we're developing a smart contract for Clipper. You'll be able to deploy that to any EVM network, and it'll be able to start participating in the Clipper system. Lots of interesting details there. Not time to go into it today, but I'm really excited about this because it gives a really great way for you to be able to integrate with other ledgers, move tokens, value, or messages between those. It doesn't have to be transferring tokens. You could have a smart contract on two different ledgers, and they just do messaging back and forward to each other. That works as well. So there's a lot of interesting, compelling things that we'll be able to do with Clipper. All right, and then the last topic that I just briefly wanted to mention is, of course, everything that we're doing is being done in the open source at the Linux Foundation as part of the Linux Foundation Decentralized Trust. And our project there is called Hyro. There's a booth over here. If you haven't had a chance to go talk to them, you can go talk to them. But we're really want to see more contributions, people coming, joining us on Hyro. In fact, all of the things I talked about today, although they are maybe the first time that we've talked about them publicly, if you were participating in Hyro, you would have already seen issues and discussions and everything else going on around these projects. There's branches for Clipper, for example. These things exist. So you can come and participate and be part of our journey, part of the Hedera journey, and contribute to open source. We've had a very successful Python SDK, lots of contributions from other people in the community, and we're working to try to increase that success across the board. So that's kind of, in a nutshell, the things that we're looking at. We're looking at making the developer experience better. We're looking at increasing the amount of on-chain programmability that is available to you, developer, to be able to develop more compelling applications. And we're looking at scalability and performance, including a whole range of different, very compelling moonshot projects that we're working on. And all of it's being done in the open source. Come participate and help the project. And with that, thank you for your time. Have a great day.
All right, thank you, Richard. That was absolutely amazing, inspirational, and also very informative. Next up, we're gonna dive deep into the Hedera EVM and also cover the topics that Ethereum developers should know about when developing and deploying on Hedera. For that, let's welcome Fernando Paris and Anurag.
Good morning, everyone. What a lovely morning we have in Denver today. Welcome to DevDay. We'll be talking about unlocking the future of EVM, specifically on Hedera EVM, for the next 25 minutes or so. I am Anurag Saxena. I have with me here Fernando Paris. We lovingly call him Fur. He has flown all the way from Spain just to be with us today. He is also Senior Director of Software Engineering at Hashgraph. He's been with us for a year and a half. And he also co-founded IO Builders. He's got wealth of experience in smart contracts, EVMs, everything to do with Web3. Fur?
Thank you, Anurag. I'm Fer, and have the pleasure to present today this talk with Anurag Saxena, which is our Director of Software Engineering. He has been with us 1 year and a half within Hashgraph. And before Hashgraph, he has been working on Amazon and mainly on AWS.
Thank you. We have a great agenda today. We'll be talking about 4 things. First, we'll start with what if building on EVM could be a truly awesome experience? The second topic would be anatomy of Hydro EVM. This is where we'll be spending bulk of our time. We'll talk a little bit about a new HIP that we have, which is built-in transaction scheduling. And we'll wind up with what is coming soon. And if we have time, we'll use that time for Q&A. Fur?
Richard introduced the concept of EVM compatibility. So as you remember, compatible means that you can run smart contracts, and being really equivalent is following the yellow paper. In our case, we are compatible, but what if building on the EVM could be truly awesome? That the protocol itself manages the heavy lifting and also has built-in features. In our case, we have high throughput, TPS, stable costs. We're also extending the EVM with built-in features like you can scale a smart contract in the future, and token services we will see around in this talk. Also, what if a performant EVM, which is performing rate, is feasible? And also, what if you can use the Ethereum community tools that you like with the experience you really want to have? No? That is what we are focusing on Hashgraph and Hedera, and it's our daily mission, and that's what we're looking for.
Okay, so let's talk about anatomy of Hydro EVM. I'll be using the term Hydro EVM and Hedera EVM interchangeably, so just don't get confused. For the purpose of this talk, they're both exactly the same thing. So what does Hydro EVM really has to offer? Okay, so these are the key offerings that we have, these 3 key offerings. Let's say you are a developer on Ethereum you like to write program in Solidity, you can write your smart contract in Solidity and deploy it on Hedera exactly in the same way as you can deploy it on Ethereum. All you have to do is just, instead of pointing it to the Ethereum endpoint, you just point it to the Hedera RPC endpoint, and it'll be, and that's it. Secondly, you get the EVM compatibility with high throughput. Okay. What it means is that you can get the Ethereum developer experience, but you're not limited by the Ethereum's bottleneck on scalability. Our Hedera network can handle much higher volume of transactions with fast finality and with predictable fees. And thirdly, you get the interoperability with the Hedera services. If you're a Solidity programmer, you can write your contract. You're not isolated to the Ethereum land. You're not isolated to the features that are offered just by Ethereum. You can take advantage of the features that exist on Hedera EVM. Just to get into a little bit more at a high level of the architectural difference between Ethereum and Hedera, Ethereum has one node for everything. So basically, it handles the transactions, it handles the consensus, it handles the search for those transactions, the data. All that is living on a single monolith. Whereas on Hedera, we've got 4 different services, 4 different nodes. First one is the JSON RPC relay, which takes your Ethereum requests. Then you have the consensus node that does the actual transaction handling, consensus, execution, etc. Then you have the Bair node, where you can search for the transaction. It's a special node that we have where the data is kept, where you can answer queries really fast. And then you have the block node, which is really the block in the blockchain. There is a talk on block node right after this to talk more about that. But the advantage of having these 4 different services is you can scale them independent of each other. You can do their performance tuning independent of each other. Our network becomes more resilient. For example, an availability on Bair node is not going to impact the availability on the consensus node, where the actual transaction handling is happening. And if you're a developer who's contributing to our Hedera repos, you get a very nice abstraction of code.
During the talk, we were going into different depths of the EVM layers, but it's important to go into different topics and differences that we have within Hedera and Ethereum that are worth to explain before we go into the layers. First of all, the account model. So in Ethereum, you have one address, which means one key. And in Hedera, we have one address means one account, but one account has multiple keys. We have multi-signature keys, we have threshold keys, we have complex scheme of signatures. That's the main difference. Then the signing keys you can use to sign smart contract transactions. We support 2 different keys. Within Ethereum, you only support ECDSA key. We support ECDSA and ED25519. And also worth to mention, perhaps we are supporting a virtual mempool soon within the relay. We are not supporting a transaction pool. It's not a distributed transaction pool. We are achieving fair ordering through ABFT algorithm. It's also important to see how we are interacting with our ledger, with our with Hedera, with the different transactions we support. In Ethereum, you have the send row transaction, which mainly is a signed transaction with an ECD key. And in Hedera, we use the JSON RPC relay for that. Then we have the special Ethereum transaction gRPC transaction within Hedera, which is an envelope, where within this envelope we have the raw Ethereum transaction. That's the construction we use within the relay to be able to manage Ethereum transactions. You can also use this Ethereum transaction via Hedera SDK. And then we have this special contract create and contract call, which allows ED keys to sign transaction within Hedera and invoking a smart contract. We also, it's worth to mention that which type of transaction we support within the Ethereum ecosystem, no? We have type 1, 2, 3, 4. Within Ethereum, we don't support, within Hydro, we don't support type 4 nowadays. We will support it soon as we upgrade to Pectra within Hydro. We are not supporting transaction type 3s because we are not supporting lobs nowadays, but we support type 1. You can either run type 1 via the Ethereum transaction, with the Sandro transaction we mentioned it before, and also we can support via the contract call and contract create, via ED keys and EC keys, type 1 transactions. And type 2 transactions are only supported through the relay through Sandro transaction.
Okay. So how is Hydro offer these capabilities? Let's look at the how it compares with the Ethereum. So this is an Ethereum client. Typically, it has a consensus layer, it has an execution layer, and it has a data layer. On Hedera, we also have a consensus layer, similar to what is on Ethereum. In the execution layer, we have Besu. We are using Hyperledger Besu as our EVM interpreter. So all the Ethereum call, all the requests, they come to the Besu. Like Fur said, that we do not have a transaction pool. The consensus ABFT algorithm itself does the fair ordering of everything, so we don't need it. The data layer, we are using Merkle data structure to store all the entities, including the account states. In addition, we have a Hydro account model. What Fur was talking about, so you have the Ethereum address, you have the EVM address, you have the account, and you have multi-key. So we have a model for that, which is very unique to Hedera. Fur?
Okay, we have the EVM interpreter, and let's go to the differences within Ethereum and Hydro. So first of all, we have our representation of a block with block streams and also a record stream. Of course, we translate to the outside world as an EVM block, but we have our custom blocks. We also have our custom state, which makes different the interpretation, the transaction consolidation. Also, we have system contract, we will see a little bit further in the presentation, which is the way we extend the EVM. That's the open door to the higher services. And that's
okay. So you can keep it. So let's look at how a flow looks like if you're a Web3 developer developing on Hydro platform. Let's say you, as a developer, you create a smart contract and you were able to very easily deploy it on a Hedera network. Now you want to invoke the functions in that smart contract. How can you do that? Okay. So one way is that you use the Ethereum community tools. You can use Hardhat, Remix, MetaMask. There's a whole bunch of Ethereum community tools that are available, which we all love and use. So you can use that to make that call. Let's say you want to make a transaction call. Okay. So when you make that transaction call, we have our own implementation of JSON RPC relay. That Ethereum request really goes to the relay. The relay is able to see that this is a transaction request. It will transform the Ethereum request into the format that the consensus node can handle. So it'll do that. It will send that request to the consensus node. The consensus node will do its thing. It'll execute that transaction, and then it'll respond back in the Hydro native response format. The JSON RPC relay will translate that response into the Ethereum format and give it back to you as a developer. Like if you do another transaction, which is maybe a query of some transaction, the request will go to the RPC relay. RPC relay will see that this is a query request this time, ETH call me. And instead of routing it to consensus node API, it will route it to Bair node. Bair node is our specialized node for searches, for any kind of transactions that you want to query. It has its own API layer. The JSON RPC relay will do that translation, give that request to the Bair node APIs. Those APIs will respond back. RPC relay will transform that response back into the Ethereum format and give it to you as a developer. So that's one way for you to invoke your smart contracts and do queries. Another way is that you can use Hyro SDKs. We've got SDKs for all modern languages. You can pick your SDK, and the SDK will allow you to make these calls. You can do transaction calls on your smart contracts. You can make query calls. And the SDK itself will be smart enough to route those calls to the right services and give the results back to you.
OK, as Anurag has explained, we have the transaction that change state, and we have the transaction that query state. No? Here we have another way of looking at the different layers. We can see the JSON RPC relay. When on the left hand, you have the Ethereum transaction. On the right hand, you can also have contract create and contract call, as we mentioned it, with the other SDKs or with the relay. The consensus node is attending the request with the gRPC API. The higher consensus layer is making gossip over gossip to receive the transaction and spread the information around the different consensus node, and then reaching the algorithm and ABFT to reach fair ordering. The execution layer is where we have our custom throttles, where we're doing the transaction handling, where we have the fees, and actually we are improving that, as Richard mentioned it before, with fees 2.0. And the important part we are focusing today is the higher EVM. And there we have the usual gas management, the opcodes, the precompiles, and the facades, which is one of the construction we will see in a couple of slides further, and the system contract, as we mentioned before, the door to the higher services, the count service, token service, the consensus service, and the scheduling service that we will see a little bit further. What's important to also mention is that the consensus node is storing in the MerkleDB all the state, and also publishing the record stream and sidecars, and the future block streams that we are going to see today in Mark's and Nana's talk. We were talking also about the transaction that occurring state. We are having the relay, which is sending information and orchestrating more or less the different mirror node REST APIs I need to call to build the RPC relay Ethereum information that I need for blocks, for transactions. The mirror node is attending the REST APIs. The REST APIs are over the mirror node database, which is built in a Postgres implementation, which is reading via a stream importer all the record stream and sidecars and the new block streams from the block node that have been produced from the consensus node level. So that's overall the different layers we have seen, which is one thing that we are seeing on the slide that was very important to mention. We have the ethcall and estimation function that the usual Ethereum node does built in. In our case, we're doing that in the mirror node through a library that we expose from the consensus node to the mirror node, which allows the mirror node to simulate the transaction and give you the ethcall and the estimation, in that case, of the gas.
OK, system contract. System contract is one of the unique things that we offer on the Hedera platform. These are really just special reserved addresses that we have, where we have the Ethereum precompiles. Basically, we have written the program for you for some of the standard functionality that is needed. You can just, because they have reserved address already, if you're writing a smart contract, all you have to do is just make the call to those precompiles using that reserved address. Okay? And you'll have that functionality right away. Important thing to note here is that these precompiles can change the state. Okay? So you got to be careful when you're using it. And on the next slide, you can see these are the addresses that we have. These are basically the Hedera features that you can take advantage of in your smart contract right away. The first one is 167. So 67. Anybody knows what that mean? OK, so 167 is the address for the Hedera token service, HTS. 168 is for exchange rate, so you can see what is the exchange rate as part of USD. There is 169, which is a pseudo-random number generator. 16A is for Hedera account service. 16B is for a Hedera schedule service, which is fairly new. So you can tell some of these precompiles will actually change the state. So you got to be careful when you're using them.
Okay, and we mentioned also what is a facade, no? There's a facade within the transaction flow. The facade is a special built-in adapter or proxy which enriches the higher entities. As soon as you can invoke a given entity with its interface. So we have here different examples, what we can build on. So there's a Hedera token service facade, which allows you to invoke an HTS token address and use it as a normal RC20 using transfer from or proof. Also, you have a Hedera account service where you can call an account address and you can invoke the special features for Hedera account service like HBR allowance or max out associations. And also the scaling service that we will see in the next slide. You can invoke the facade and also the system contract, but in this case, you can invoke a schedule entity and sign a schedule or delete a schedule.
As you know, we are having a scavenger hunt, so
Here's the next
chance
code.
to gain some points for that.
Yeah, good luck. One important thing is, after we have seen all the different layers, to summarize which are the key differences and also the benefits of using higher Hedera. No? For sure, everybody know that we have the ABFT higher consensus layer, which makes the fair ordering, the static pricing, the stable pricing, and gives you all the TPS and throughput that we are nowadays having. We have the Merkle DB that we mentioned it, where we are storing our customized Merkle tree into the database. We have the networking, gossip over gossip. We have the streams that we mentioned, the record stream, the sidecars, the block streams. That makes a difference. We have the mirror node, which is a full node within the Ethereum world, which is more queryable. It's more friendly for being able to get the information. For sure, we are extending the features via the system contracts and enhancing the EVM, as we saw with the system contracts and also with the facades. We have no mempool. We have a furthering built in. We have a special difference between Ethereum and us, which is the account model. As we mentioned before, we're supporting different keys. We have account versus a key model that we mentioned before in Ethereum. And also the different transaction layers that we have, which allows us to work on gRPC, but be able to bridge it to the Ethereum world. We usually get the questions about how we are evoluting the EVM, because we have special differences that makes us really special and make the difference and makes this evolution of the EVM and this lovely experience possible. No? When we have a new higher services implementation, we need to expose new system contracts or new function selectors within the system contracts. That's how we evolve the higher EVM in one sense. On the other hand, we upgrade our EVM with the Ethereum forks. But why we are not following Ethereum schedule? Well, we have seen the differences. So first of all, we wait until the fork is actually released, it's stable, and it gets the right adoption within Ethereum. Secondly, we investigate, research the EIPs included into a fork to actually map then which ones touch our different layers and which are meaningful for the Hedera community, for the higher community. Once we have them identified, we test them out, we implement them. We need to implement the higher improvement proposals. Depending on the complexity, it's a more global HIP or it's a more detailed HIP. And then we implement it, we test it, and we roll it out. That's the reason why we are not following the schedule, and usually we are between 2 quarters or 3 quarters ahead. And as we mentioned it before, we have this system contract, which is the open door to our higher services, which make the difference. Today there's a talk that's going to talk about scaling, but I want to really open the floor with that part. It's truly awesome that you can, with Hyro, schedule a contract in the future. In Ethereum, you cannot do that. You need to rely on external providers like Gelato, like Ethereum Alarm Clock or Chainlink. And within Hario, you can do it with via simple system contract built in. You call the system contract with the call data, with the address of the contract you want to call, with the given gas limit you want to schedule, and the network cares about all that stuff and makes the leverage of that part without needing any external provider.
Okay, so stay tuned for some of the big things coming. We are working on EVM Pectra upgrade. It should be coming out very soon on mainnet. We're working on blazing fast EVM. Richard had a moonshot goal for that, but we are continually working on improving the performance. We are working on an EVM block explorer, which will give you a very similar experience what we have in the Ethereum world. We're working on making HTS look exactly like ERC. So, if you're a developer using HTS, you will be you'll have no difficulty picking it up. Delightful developer experience, we're always looking at that, what we can do to make it really sticky and very easy for the developers to pick up. And Clipper, what Richard called out as another moonshot, that's something that you'll hear quite a bit about. It's the built-in cross-chain interportability. So those are some of the big things that are coming. With that, I think we're going to stop here and take any questions if you may have. And if not, Ford and I will be, oh yes, please.
I'm just, curious, so the MEV problem in Ethereum and Solana, right? That people can reorder the blocks to kind of attack other transactions and gain value, stealing value from the other transactions. What's like the core thing in Hedera that prevents that problem? And what's really like the design aspect that prevents that problem that gives you an advantage?
In Hario and Hedera, we have the ABFT algorithm that takes care about that. It's a fair ordering, asynchronous. Nobody can intercept that or try to change the order of the transaction. You send it to the network, and asynchronously it will be built in the order. So nobody will be intercepting that. That's the main difference. We are not, as Richard meant it, so I mentioned it before, there's no leadership there to really put the transactions in order. It's an asynchronous Byzantine fault tolerant that makes this totally stable, and you're not intercepting that part. Nobody's taking care of that. It's the algorithm is taking care about the ordering.
Michael?
Yeah, it's the random number generator and the PRN, the random number generator function contract. Is that good enough if you were to use that in conjunction with KIP 1215 to, let's say, make some sort of self-recurring autonomous lottery? Would it be good enough to draw a random number, or could that be predicted in some way?
Nowadays it's good enough.
I'll just repeat the question. So the question is, the precompile that we have for pseudo random generator, can that be used along with the HIP 1215, which is built-in scheduling for transactions? And the answer, I think the simple answer is yes. But if you want to add something more to that.
No, it's good enough. It can be improved in the randomness generation, but you can use it nowadays on the scheduling service without any problem.
Like for a lottery?
For a locker.
A lottery?
A lottery, yes.
Yeah, autonomous lottery
Yeah, as example, in our demos, in the engineering team, we are using that lottery to start who is going to start within the team. So we're using it on a daily basis, so you can use it. Piotr, you had that question?
What is the biggest challenge that Hero that you will need to
Okay, so the question is, what if you were to pick one challenge on Hedera EVM, what is that one biggest challenge?
That's a good question. So I think if I need to pick one, how to extend the developer experience overall. So the ones we have been here for a long time in Ethereum. I've been here since 2017. I suffered a lot the different tools that were there, and we're still missing a good debugging tool, the transaction, where you can trace the transaction, debug it. We have Tenderly, but something built in the IDE, or something you can really debug is something we are missing. There are a lot of things on the deployment part that can be improved. So that's what I'm thinking that's the most challenging part, which is going way further than the existing tools are. That's what I would mention. Aside the fastest EVM part, which is part of the moonshot, but if I pick one, that's my pick, the developer experience.
Okay, I think we're ready for the next talk. If you have any other questions, we're going to be hanging out here all day. So feel free to approach us.
Thank you.
Thank you.
All right, thank you, Fer and Anurag. That was absolutely amazing. A great deep dive and overview of the architecture of the Hedera EVM, the smart system, smart contracts, and so much more. Now we're gonna go deep into one of the most important topics for 2026. That's gonna cover major network upgrades that are gonna impact decentralization, also network performance, and how developers access data from the network. Please join me in welcoming to the stage Nana and Mark.
All right, good morning, everyone. All right, so welcome again to Hedera DevDay. We're really excited to talk to you about one of the biggest upgrades that we've done on Hedera. So my name is Nana Sophie Kondia. I'm a director of software engineering, and I'm joined here by my PM partner in crime, Mark Blackman, senior director of product. So we're going to tell you a bit about the upgrade, why we're doing it, why we feel it's necessary. We'll dig into some of the details of that around block proofs, TSS, things that you've heard about a little bit, but we'll dig in, block streams, block nodes. And then we'll really tell you, especially for the mirror node operators, how will this impact you? What do you need to do? What do you need to pay attention to? And then the same thing for developers in general. What can you do moving forward with these new capabilities? And then we'll conclude there. So you're probably looking at the slide and wondering, why is there a jet engine on here? You thought it was a blockchain talk, right? So this is how I feel about the project. This is sort of the gravity of the situation. Imagine that you're in a large aircraft. You're carrying commercial goods. You're carrying people. Right? And then you look back and you're like, wait, we've been operating since about October 2019, so 6.5 years of good operations. We've gotten to really high heights and really good speeds, but we want to go further. But we cannot afford to stop this plane. We have to keep moving. So to me, it feels like we're being asked to change the engine on the plane as we're flying it out. So if you think about the network today, the data and the output is sort of expressed as an afterthought in static files in central locations that you can acquire for a little bit of a cost and you can verify with some extra effort. Where we want to move to is a network that expresses its stream of consciousness as it goes along. Anybody can kind of subscribe and tap in there. They can store it where they like, and they can simply and easily verify it. So the goals here, if you remember some things, it would be that we want to increase decentralization, reduce costs, and reduce the latency as well. So today's current network, we have our consensus nodes. They receive transactions. The main goals of the consensus nodes are to receive those transactions, gossip them out, and order them fairly, right? Everything else that it does is extra, but those are the main things that it should be doing. So today, each of those consensus nodes upload multiple files, multiple streams within those files, right? So you have the record files here, which include the transaction input and some of the changes around it. You have the signature files, which are essentially saying each of the consensus nodes have taken a record file, they've hashed it up, and if you collect enough of them, you can confirm that there's consensus or enough of the consensus nodes agreed on the details of those record files. You have the event files, which are saying the details around consensus and how fair ordering happened. You have the sidecar files, which have all the details about all the amazing EVM stuff that you heard before. And then you also have safe states. All of these are pushed up to GCP, AWS, and other cloud buckets, where mirror nodes that you come to rely on today can download those, right? So you can see that there's some improvements that we could do with this working system, right? There are multiple files that people have to take, sort of capture, multiple streams within those files. So do you need today's file? Do you need yesterday's file when you're looking for your data? The consensus node, like I mentioned, is doing extra effort. It's not just doing gossiping and fair order, and now it's having to worry about sort of uploading all these different files, right? There's also dependency on these cloud storage vendors, end-to-end delays. Even though it's in seconds, and we're very proud of that, it's, a second is longer than a millisecond, so it's something to note. There's some state data isolation. Not every mirror node has all the information that it needs. If you've started a mirror node and wanted to start from Genesis, you know that there's a bit of coordination that needs to get there to play all the transactions. There is some data duplication in the record file and the event files, and so we would like to improve that. And then, as I mentioned, if you want to verify, you actually have to get a couple of different file types, the record file, the signature files, and you have to coordinate in there and finally get the verification going on. But I want to be clear, right? We take this very seriously. We are never going to do sort of an upgrade at the expense of any of the amazing things that you've come to rely on. The network that I'm talking about that we want to improve is the network that has brought you 10K TPS, it's brought you 1 to 3 seconds finality, it's brought you 7 to 10 seconds end-to-end latency. So this is a serious network that is doing a lot of good things, and it's nothing to sort of disregard. But if you know anything about Hedera builders, you will understand that we're the type of people to say, what got us here today is not what's going to get us there tomorrow, and so we're willing to be audacious and push the boundaries here. So we want to move the network, as I mentioned, to say that the consensus nodes now output a single stream, right? We had multiple before, now it's a single stream, and it's fully expressive in terms of what happened on the network. Now, instead of going to these cloud buckets that we had mentioned before, they go to this new node type called a block node. That block node can now store, verify all that information, both locally and remotely. And as Richard had mentioned before, as the information is coming in, the block node is sending it right across. So you don't have those extra latencies that we spoke about before. Mark will expand a bit on this, but as a single block item comes in, we can send it out, as well as in the background, building up that block and verifying it. So some improvements that you'll immediately see is that we've consolidated the streams. There's now no longer 6 different file types with a long stream. Everything is in that single stream that you can listen to, right? The consensus node now doesn't have to do so many tasks. It can begin to focus more on fair ordering and gossiping, as I had mentioned. Verification is actually made very simple. Mark will expand on this, but all you need is that single block item, or that single block with all the block items there to verify it. So one file you can use to cryptographically verify all the trust that we in the past had to do multiple steps for. We've removed that dependency on centralized, cloud buckets. You now have decentralized storage. We can have lots of companies. Hopefully, some of you here, including myself, will run block nodes in the future. Reduce end-to-end delays, as I mentioned. Now we're going to be talking about milliseconds instead of seconds. And you'll also be able to have off-chain state, right? As you're listening into this block stream, you'll be able to have the same state that the consensus node had built up before. And we've also been able to duplicate the data as well. So how do we get there? It's a lot of work, but 3 big tenets that we're relying on. They're all big HIPs that you can go out there and read on the HIPs network. So HIP 1200 TSS, so this is the threshold signature scheme. Summarize, this is just a constant size aggregate signature that will help you easily verify a block and the details within it. Block streams, again, that full specificity of all the details that went into the transaction, the changes, the state changes, everything is in there. And then block node, this is where everything comes together in a decentralized fashion to be able to store, but also to do more. So I'll hand it over to Mark to talk about block.
Thank you, Dana, and thank you all. Very excited to talk about these 3 technologies here. I will start off with block proofs. Block proofs, as Nana mentioned, are replacing the individual RSA signatures that each node signs each record file. It's transforming that into a network-wide signature, which has a lot of very valuable properties. It makes blocks self-contained and independently verifiable. That is a huge part of this whole solution here. Is these blocks are independently verifiable without the network, without a node, without being online. You have a library and a block, and you could verify it. The proofs themselves are very compressed and very low cost. We do a lot of the upfront processing in creating the proofs so that the verification of the proofs is cheap and quick. Additionally, these three HIPs make mirror node operations much cheaper and much easier to facilitate. And then again, the proofs are very inexpensive and low cost and constant size. So no matter how big the network gets, how many years the network runs, the proofs will remain the same size. So this is a visualization that really demonstrates the before and after. As mentioned, we had a multi-file operation that was required to verify transactions and records. And this process was complex enough that we just trusted the mirror node to do this for us. But the mirror node itself is an untrusted node type. And where we've gone is now the trust is in the data itself. You can see on the right-hand side, we have a block. That block proof, no matter what block you get from any node on the network, is going to be the same, and you could verify that. And the strategic timing of this is really impeccable as we move from mass usage and really RWAs and safe, the world's safest assets are now going to be moving to our rails. The network receipt has been upgraded so that if you're making that large purchase, you'll be able to archive that receipt and verify it at any point. Before we get into the details of the block proof, I just want to explain a few concepts to you. First of all, aggregated signatures. This is when multiple signatures are used to create a single aggregated signature. So in our case, each node will be signing the block, but that will consolidate up into a network-wide signature. Additionally, we have the concept of threshold signatures. These are already supported on the network. I actually took this from Hashscan, but you can see in this case, there are 6 signatures and 3 are required to produce that aggregated signature. So what our block proofs are aggregated threshold signatures or proofs. And these proofs are used to verify the block itself, but also you could independently verify any element within the block, any piece of data. It verifies that the blocks were signed by a majority of the network. And when I say majority, I'm not talking about a majority of nodes on the network. I'm talking about consensus weight. Consensus weight is derived from staking delegations and really enables certain nodes within the network to have more functions and more operations within consensus. And indeed, this is an example of just that. Blocks are produced separately on each node, but you could grab any block from the network and that proof will be the same. So again, the blocks are independently produced, but the block proof is a network-wide proof. And with these block proofs, again, blocks are independently verifiable. So let's break down what TSS is and this suite of encryption technologies. Firstly, we use BLS, which is fairly common in our industry. That's what's used by Ethereum and others for nodes to attest to the output of the network. However, in BLS, for us, there's one serious limitation, and that is all the signatures carry the same weight. And as we mentioned, we are dealing with consensus weights. One node can have a different consensus weight than another. So we've added this layer on top of BLS called hints. And Rohit and Leemon will come on next to give some more details on this. But this is what provides that weighting differentiation between blocks. And in our case, it's able to represent the 64-bit consensus weight. And then finally, as mentioned, we have consensus weights and nodes on the network. However, how do we verify what nodes are on the network and what their associated weights are, or even their signing keys? This is what we call wraps. And this is essentially a recursive snark proof that is generated each time the address book changes. And it's recursive in the sense that it goes all the way back to the Genesis address book. And as mentioned before, this is a constant size proof. So no matter how many times that address book changes, the size of the proof will remain the same. So let's look at it in action. If you see on the left-hand side, the first step is really to verify what the network is, what nodes are on the network, and what their weights are. So this is a fairly intensive operation, can take upwards to 30 minutes. But what's important, this is only done each time the address book changes. So on average, nightly, after the staking delegations are calculated and consensus weights are updated, then we will produce these wraps proofs. And again, with that upfront processing, it makes verification much cheaper and much quicker. So we're doing that upfront. And then once we have that proof, we're able to use the information within the address book. And so the nodes, the weights, the signing keys are sent to the BLS hints part of this process. And it's here nodes produce blocks, and they exchange the blocks just to make sure they're all producing the same blocks and consensus is matched, just as is done in the current consensus algorithm. But once they get to a certain threshold, a configurable threshold of consensus weight, then the block is valid. And at that point, the block proof is generated, and downstream components, such as the block node, are able to validate that that block has been indeed generated by a majority of the network. And again, this is a very lightweight proof. It has 3 components. One is the hints verification key to verify the hints layer. The hints proof is used with that key. And then finally, that wraps proof. So it's these three pieces of information that are used to actually validate and verify the proofs. So just to recap, I just want to say block proofs replace the existing RSA signatures. It's an aggregated threshold signature. BLS and hints are used to verify blocks and ensure they're valid. Wraps proof are to verify the address book information. And the whole proof itself is less than 3K and executable by a smart contract. So now let's get into block streams. This is the new data format for what we're doing. This replaces the existing record format, and additionally, as Nana mentioned, it replaces the series of streams we have going out of the network. It provides self-contained, verifiable blocks of data. It consolidates all those separate streams into one single stream, giving you a consolidated view of the network. It helps with the cost optimization. As I mentioned, mirror node operations is greatly reduced and the cost, less end-to-end latency. And then, as has been mentioned by Nana and Richard, we begin processing, and after a single transaction is processed, it's out the node so that downstream clients can begin pre-processing that data even before the block proof is produced. So let's get into block streams. Block streams is a stream of block items, and you could see on the diagram here, we have a few different block items. So how we consolidate those different streams, whether it's records or events, you could see here, those are each individual block items. And a series of block items are repeated for each transaction. You could see in the middle, the event transaction the result of that transaction, the output of that transaction, the resulting state changes of that transaction, and then any trace data if it involves a smart contract. Once the transaction is processed, these are sent on the wire. And so that end-to-end latency is greatly reduced. And as I mentioned, this is a full scope of the network. So as events are created, we send the events. As consensus rounds come to completion or start, we're sending those round headers. And so it's a culmination of all these things that make up the block stream. So let's see it in action. On the top here, you can see what's being sent on the wire. The right-hand side is the first sent. So that block header is what's sent on the wire. And then you can see there's a series of block items. In this particular case, if you look at the larger picture, you could see that this block is reconstructed by the block node. So the block node will receive these block items and then reconstruct it into a block. In this case, this example is a block with 2 events, 1 transaction each event. So again, these are sent in near real time, and the block node will reconstruct those into blocks. And it forms a blockchain. The previous root hash of the block is in the current hash, and et cetera, et cetera. Now, these block items are reconstructed into a Merkle tree, and that's very important. This is not just a running hash, but we're actually taking those block items, putting it into a well-structured Merkle tree, hashing all the way up to that tree, getting the root, and that is the identifier of the block. That root hash, again, is in the next block, et cetera, et cetera. But additionally, we're also keeping an historical record of all the block hashes ever produced. This enables for one block to be able to prove all the historical blocks before it. And the consensus node and the block node are keeping a historical record of all of these block hashes ever produced by the network. So here's an example of that Merkle tree I was just talking about. It's a well-formed, well-structured tree, and the block items are at the end of the tree in these virtual maps. So for example, you could see node 13, it says the root of inputs. So these are where the transaction block items are formed into that tree. And as mentioned, this whole tree is hashed up to the root, and that is what the nodes are signing. However, we could actually verify specific data within that block. We call these block contents proofs. This could be a transaction input, this could be a state change, this could be anything within that block can be verified. So in this case, we have transaction 1 at the bottom, and we want to verify with a block contents proof that this transaction is in this block. Very simply, we hash transaction 1, transaction X, and ensure that that equals node 13. Likewise, we take node 13, node 14, hash it up to node 7. Does it equal node 7? Yes. And you do this same operation all the way up to the block root, and then using that block proof, verify that that root is in that proof. So this is what makes blocks independently verifiable. And what really is exciting to me is it's not only giving you record that the transaction has been processed by the network, additionally, it gives you a verifiable indication that that record, or the output of that transaction, was applied to network state. So this is very, very important. I think market leading in the fact that we're not only verifying that the transaction took place and the nodes processed that, but that they indeed did apply that to the network state. Speaking of state, as mentioned, the fact that these state changes are in the block node means that other non-consensus node types or even smart contracts will be able to maintain state or verify specific elements of state outside of the consensus node. This is a huge benefit for many reasons. But let's look at the example first. In this case, address XXX is sending 2H bar to YYY. And so we would get that transaction and the output of that transaction in the block stream. But additionally, we get the resulting values of that transaction. So you can see in this case, 2 H bars was taken from XXX and applied to the balance of YYY. So it enables the block stream to not only express the transactions, but then also the resulting state values of any elements that were changed. And this again allows you that next level of verification, but it also enables us to service block proofs, state proofs within the block node. Additionally, allows us to take a lot of these state services that were in the consensus node, such as reconnect or resync with other nodes, and have those hosted on the block node, freeing more resources for consensus nodes to focus on consensus and scale the network, continue to scale the network out. So very exciting aspect to this, the fact that we're adding that state data to the block stream. There's a lot of benefits with all three of these HIPs. I'll mention, we've mentioned the end-to-end latency. This is one example, one specific reason why this end-to-end latency is being decreased. Currently with a record file, that record file stays on the consensus node for 2 seconds. And then at that point, the file is created and sent. Now that's up to a 2-second delay even before it leaves the consensus node. Additionally, that means the output of the network is based on wall clock time, but consensus node it runs on consensus time. Many times, currently, you could have a series of transactions that were actually executed in different rounds of consensus, or even the same round of consensus, but ends up on 2 separate records. So one round of consensus can span multiple records. With the block stream, blocks are one or more rounds of consensus, so that consensus time and the consensus round boundary are preserved through the output of the network. So it's a dual benefit there, decreasing the time, but then also making consensus time and rounds consistent with the output of the network. Additionally, we have better filtering. These block items are already pre-filtered because we're breaking them out into little chunks. But then also with the block node, you could choose to filter either what types of block items you want to see. So I only want to see transactional outputs, for example. Or in the future, and we'll get into this, you could actually filter by an entity. So I only want to see the output of operations that have impacted the accounts I care about. So better filtering also here. So in recap, the block stream consolidates these multiple streams we had before. A block stream is just a stream of block items. They are processed with low latency and immediately sent on the wire. They are constructed into Merkle trees, providing built-in validation. And then they also have included state changes. Here you go, Noah.
Thank you. So with all of that, we've seen the advancements of TSS, we've seen the advancements of the block streams. Now these all come together on the block node as well as the consensus node. So in this new form, we have, again, the consensus node pushing out a block stream to a block node, storing that process block locally or remotely, again, forwarding those block items immediately off to mirror nodes and other dApps, And then those dApps also being able to query the block node for whatever APIs that are made available. Mark mentioned Reconnect, so that's also another connection that you can see from the block node to the consensus node. And this, I'll go into this a bit more after, but this offloads a couple of resources there. In this one, you'll see that I pointed out tier 1 and tier 2, and this is important. Any block node that receives block streams from a consensus node is considered a tier 1. And these will likely be hosted by, operated and hosted by council members, as we've done with the consensus node. And so each consensus node, we hope, will have a dedicated block node that will receive its block streams and therefore its blocks, right? One of the main things that the consensus node will want to verify is that the blocks that it's producing have been put out and have been secured. And so block nodes at tier 1 will be serving that purpose. Anything after that is a tier 2 block node that anybody, the community and others will be able to host, and then you'll see some really interesting stuff come from here. So there's a lot of different services that the block node could offer. I'm calling out a couple here in 3 different categories. So the first is the core network offerings or services. So processing block streams. As we mentioned, as the block nodes come in, the block streams come in, the block node will aggregate up those items, build the block, and verify it with TSS. It'll then do archival processes where it will either store it locally in optimized fashions, or again, for remote purposes like disaster recovery, you can also upload it into different remote services. A new service that it's going to add is that it's also going to maintain state, right? So that same state that the consensus node has comes to consensus and gossips out. The block node will be able to reproduce that state and maybe be a few, maybe nanoseconds or milliseconds behind because of the propagation of the block streams. But it will be able to maintain that and create snapshots and give that out. Then there's the distribution services. So not only will the block node store those and have that information, but it wants to be able to pass it out to the community, to mirror nodes and to other dApps. It will push out block streams to anybody that's subscribed. It'll also provide block services and being able to feed up a single block, right? So if you wanted the raw information about a block, we can give that to you. But of course, continue to pull from your mirror nodes if you want the indexed, nicely massaged and refined information. But if for some reason you wanted that raw details, you could pull any block from a block node that has it. It'll also have state services, as I mentioned. So at some point in time, you will be able to query, say, hey, I want my entity. I want the full entity. I want this account. I want this file. I want this smart contract. And maybe I want to add a specific block in the past, right? You'll also be able to pull out state snapshots that were taken. And then we have the value-added services. These are the things that we weren't able to do before, but we now can because of block streams and TSS and others. So we can provide you with state proofs. We can say that, hey, my account had this balance in the past. You can take this and then you can sort of prove this cryptographically without a doubt. You can also do things like block contents proof, which says that within a specific block, there was a transaction, or maybe there was a state change, maybe there was an event header. There was a block item that was contained in this block, and I can prove it as well. You'll also be able to do things like filtering, as Mark mentioned. So depending on the tier, a block node could say, I'm only going to store, let's say I'm a DEX, right? And I have a specific block node. I can say, I'm only going to store the transactions and informations that relate to my DEX and any entities involved in it. That way I don't have to store the whole of history. But I can also make it so that anybody that subscribes to me or requests details can have that filtered details out, right? And so it allows dApps and others to now really focus in on what's important to them. And then, of course, the node status should be able to expose on the block node side what all blocks it has, what services, and other items. So you've heard me say a lot of things that the block node can do. We will hash up the different block items into a block, and so this is going to ask for really high CPU specifications. We're also going to maintain state, so that's high memory advancements, right? And then storing all of those blocks and those states is going to ask for a lot of space, right? So at a hardware level, the block node is going to ask for a very interesting profile that many others don't have, right? We're going to be asking for high CPU, high memory, and high storage, right? And we want that to be highly available. And so over here as an engineering team, a product team, we've had to make some interesting design choices to ensure that this can scale with everything that Richard was saying. Remember, he said we're not going to stop at 10K TPS. We're going to move to 100K TPS, and in the future we want to do more. So we have to ensure that at no point in time is the block node the reason that you cannot get your transactions and everything else faster. So one of the choices that we made is for the streaming purpose, we chose gRPC over HTTP2, right? So we really want to be able to push those block items out really quickly. We're talking nanosecond, millisecond regions, right? We also, as a team, are very strict on the frameworks that we choose, right? It's for a security purpose, but also from a profiling and performance standard. We want to make sure we know every single dependency that is in there. So we don't just take something off the shelf. If we can build it, we will. But if somebody has done it well and refined, we will pick that up. So an example here is Helidon. We did some research and we decided to use Helidon because of their lightweight frameworks, right? And so for there, we're able to offer a really lightweight web server that can function well. We also decided to pick up the LMAX disruptor dependency, and we use an event-driven logic there. So the idea here is, how can we make sure that the items are going through as quickly as possible through the block node, right? Can we do this in a non-blocking fashion, right? How sympathetic to the hardware can we be? We will make all those choices that look at different layers of memory, and we want to ensure that you are getting your block items as fast as possible, right? We are not the blockers. And then finally, we decided to go with a plugin architecture. This means that in the past, you've had to wait for either the block node, or let's say the consensus node or the mirror node team to develop a feature before you as developers could do it. Now, with the plugin feature of the block node, you should be able to develop that thing before anybody else. If your use case demands that a block item or a block be produced in a different way, you can now do that. So let me expand a bit on the customizable plugins. So here's an example of a block node with some plugins. So there's a backfill plugin. This plugin says that as a block node, hey, I thought that I had that block, but I am missing it. So does anybody else have it? If you do, I'm going to go out and acquire it. We have things like the verification plugin, which says that I can use TSS to build up that block and verify it. We have things like state management, again, which will build up different state, the Merkle tree of state, and allow you to be able to query from it. But at the end, I've left those 3 dots there. And those aren't saying those are more plugins that we have specified. Those are saying that those are plugins that the community can specify. And it's as easy as implementing this interface that I've highlighted here. So this is a Java example. So really, all you need is to implement this interface with 3 functions, an init, a start, and a stop. And you can dictate what APIs you want to expose. You can dictate how you want to process the block items and how you may want to store your blocks or your state. So what does that actually look like? So here are 5 examples of profiles of a block node. So the top is tier 1 local full history. This is likely what every council member will be running. They have the publisher plugin. They have the block access, local storage, status subscriber verification, and state. So they will be doing this to ensure that they can back up the history of the network, right? We then have a tier 1 remote full history. And you can see that the only difference here is that local storage is now remote storage. But you can already see that we're swapping in and out a plugin. So let's go to a tier 2 local full history. You can see that this one is missing the publisher plugin because it is not receiving block streams from a consensus node. So it doesn't need that plugin. So already that profile of a block node is smaller and can be more performant based off of your use case. It also allows you as an operator to decide what type of hardware you need. In the tier 1 case, you might need something very beefy. At the tier 1 case, you can go a lot smaller. You only need what you need, right? And then we get into the custom cases. So tier 2 custom block nodes. In this case, somebody could say, hey, I only care about blocks. I really don't care about state. But I want to be able to do it in the way I want to do it. So you might have a custom access or a custom storage plugin that says that I am going to feed up blocks with maybe extra parameters that the usual block node doesn't have. Or I'm going to index it in a way that makes sense for my DApp, right? You can also have a tier 2 state-only plugin or a block node that focuses only on states, doesn't really care about the blocks themselves. It streams in the block items, but it really focuses in on creating custom state, offering up proofs and others. So really, the power moves over to the developers. So early on, we had spoken about offloading some state services from the consensus node. So now the block node is able to build up state. And one interesting factor here is that when you're maintaining state, it actually ends up being 2 large Merkle trees of state. There's one that is the latest verified state, right? We've run the TSS verification, and we're happy with this last one. But as the block items are coming in, we are building the most recent one. And so we're able to take that away from the consensus node where it doesn't have to do it to rely on others. It can do what it needs, but we can do this and be able to feed out information. We can then take snapshots and create those locally, have those backed up at certain cadence. We can then also provide different details around state. You can pull your entity if you like. We can store those remotely. And then finally, we'll be able to provide things like state proofs at different levels. Another one that we had mentioned before is reconnect. So it's really important to understand that every time a new consensus node comes online, or maybe for some reason falls behind, today it goes to ask other consensus nodes, hey, I'm missing information. I need it to be able to take part in consensus. Can you give me all that data? And therefore, a consensus node has to do this heavy bandwidth process of being able to give you the latest snapshot and all the event information before that. Now, a block node can take over that process and say, for a new consensus node on the left, it can ask for information, and the block node can provide it the state snapshot and all the streams of block items since that snapshot to be able to catch up. Or if on the right, it's a consensus node that's fallen behind, you don't need to pass it a state snapshot. You just give it the block items that were given from the last time it got a state snapshot. So what does this look like across different tiers of propagation, right? So the consensus node feeds out block streams to a tier 1 block node that is focused on network integrity and high availability. Tier 1 block nodes can now focus on really community scaling and adapting the block items or the consensus, sort of the logic to a dApp or to a mirror node. And so just a recap there, a block node is going to bring the ability to remove that dependency on cloud buckets. They will be there based off of your scenarios, so remote backups if necessary. We also bring in improved state service offerings, and we augment the reconnect service so that it's more lightweight, but the consensus node doesn't need to serve that purpose. There's real-time propagation, so again, as a block node is getting block items, it's feeding it right out. You're going to be able to extend the operations of a block node. And then also what I'm really excited about is there's going to be a new node economy, right? So tier 2 block nodes can then begin to decide, how do I charge for my services, or how do I talk to other block nodes, right? And for the scavenger hunt, you have another code here, so quorum. All right, so who does this impact? First, the mirror node operators. If I say nothing else, and you remember nothing else, mirror node operators, you will need to upgrade. You've got to keep up here, right? It's the one thing that's going to bring you a lot of effort. Don't sleep on this, right? So benefits to mirror node operators. You're going to have simplified TSS verification. You're going to be able to reduce your latency as you stream. Mark had mentioned that 2 seconds that you needed to wait before. Now you get a block item as soon as a block node gets it. You're going to get that one before. So let me put that in perspective for you. If you're doing 10K TPS and that first transaction comes in, a mirror node could receive that first transaction before the 10,000th transaction comes in. And so you're able to do a lot of early pre-processing, right? You'll have things like reduced egress costs. And so holding that data yourself, you don't have to pay a lot of those cloud fees that you had to do before. You're going to have explicit access to state changes and retrieval. And you're also going to be able to sort of deploy your own block node at tier 2 if you wanted to. So again, a mirror node operator could say, hey, for me, I want to be able to call a couple of custom endpoints. So I'm going to host a block node on my end on tier 2 side, and I can connect it to there. And so we're hoping around Q3 this year that will be possible. All you would have to do is deploy your tier 2 block node and point it to either a tier 1 or a tier 2 block node. So what does the cutover actually mean? Right now, as we speak, the block node software is there that you can run if you wanted to. You can start to begin to experiment with that. By the end of Q1, we're hoping to have a mirror node that supports the block streams and this whole process. And so we would ask mirror node operators to begin to experiment, like Richard had mentioned, use Solo, deploy it, make sure that it works for you. In Q2, we want you to upgrade. Upgrade to that minimum version, but throughout Q2, pay attention, get the latest mirror node version that you can, and get ready for that cutover, right? Once that cutover does happen somewhere in the mid-year, it should be as simple as, if you have that minimum mirror node version, you would be fine. If you wanted to specify which block node you wanted to point to, then you can do that as well. So for developers, what does that mean for you? I'm happy to say that if you're pointing to a mirror node that is supporting those block streams, it means nothing. You don't have to do anything. You don't have to worry about it. You're going to get low latency almost immediately once that upgrade happens. But there are a lot of things that you can do, right? So you will begin to see over time the SDK have new APIs that you can use to take advantage of these. You'll be able to start to play around with different cryptographic proofs that give you that reality and that trust that you were looking for. You can build real-time dApps, and you'll be able to take advantage of the plugins and the tier 2 hosting. So classes of apps that we couldn't do in the past, or maybe we could do, but they were on the seconds level, now you can do at the millisecond level, right? High-frequency trading apps, things like gaming and IoT, we think those could become possible. So some real-world applications. You guys have probably heard about, on-chain escrow. This can happen today, but it can happen nicer with everything that we're talking about. So let's say a family does want to use this smart contract escrow service. They can issue that 500K purchase over, right? The smart contract has that logic. The deed owners can now issue that deed transfer, and between the two of them, now you have complete blocks that specify all of that information. The offline verification can now be done. Literally, you can now take it to the bank. You can take it on legal disputes and others, and have those self-contained blocks express everything. And with that logic, the smart contract will be able to hand over these different details and manage that. IoT logistics can also become more interesting. Let's say you have 10,000 trucks that are pushing information out. If you had a tier 2 block node, you could have, let's say, a agentic agent that's thinking about your interest. It's filtering the streams. It's looking out for, hey, where are the, if it's about temperature or anything else, where are these values falling, and is it holding my business interest in heart, right? You can then do the TSS validations and then update your backend APIs in real time, making that available to your customers. Another example might be DeFi trading. So as we're doing HBAR to HTS swapping right now, in the past, you may have taken some sort of guesses on the trust. Today, you'll be able to say, or once block nodes are out there and that block is there, you can say, within that block, I can do a block contents proof that says that that swap actually happened. Within that block, I can prove cryptographically that is in there. And so you can begin to do instant trade validation.
So you could advance it. So in conclusion, 3 HIPs are really driving this. We're updating the cryptography as we discussed, the actual data formats, consolidating those streams into one stream, and then finally adding a new node type, the data lake of Hedera, and Hyro, the block node. This is happening this year. As Nana mentioned, mirror node operators, you will need to update the mirror node to a compatible version, and that is coming in Q2. And then by mid-year, we are going to be making this cutover. So again, it is cutting over the data stream itself. We're adding a new node type, and then the trust of the network, the cryptography we use, is also going to be cut over. So that mid-year cutover is a really big deal for us, and we're very excited and look forward to doing it together. Thank you all for your attention.
Thank you.
All right. Thank you, Nana and Mark, for that amazing deep dive into one of the most incredible innovations for 2026 for the network. That was a great overview of TSS, Blockstream, and block nodes, and certainly looking forward to the next session. Now, before we go into that, did anybody lose their phone? Never mind, that's my phone. Now that I got your attention, I want to point you to the next session, which is very special. It's going to be a fireside chat covering very interesting topics. You're going to hear keywords like quantum, TSS, cryptography. So please join me in welcoming to the stage Dr. Leemon Baird, co-founder of the Hedera Network, and Hashgraph Head of Cryptography, Rohit Sinha. Thank you.
Thank you. So I am really excited to be here today with Rohit. You're our head cryptographer, and you work with Protier, and I know you work with academics at other institutions. You've invented cool things, and I thought it would be fun for you guys to talk with him and to hear him. And I thought it'd be really interesting to hear about some of the stuff you've invented that we are now putting in TSS. We've heard about TSS. Tell us about it.
Yeah, we can talk more about TSS. It's something we've been working for quite a while, making improvements, finally at a stage where we can say we'll be able to release it in a few months, so it's a pretty exciting time. So yeah, going off where Mark and Nana left off, TSS is our proof system for attesting to a higher block. It's basically, in a nutshell, proving that a threshold fraction of an address book has signed off on a given state, which means, and a threshold, you can think of it as, like, let's say half. Half of the address book by weight has signed off on a given state, which means that if there's a subset of adversarial nodes, they cannot forge invalid blocks, and that's a pretty important security guarantee to have. And we're not the first people to study this problem. State signing, a lot of folks have looked at this problem, and oftentimes we find that typically the way they approach it is they would the participants on the chain, they would publish a set of signatures, and in order to verify whether those signatures are valid, it's your job to look at what is the address book at a certain point in time, and you could typically trace that by looking at block headers, going back in time. And what we feel is, ideally, from an end user or from a developer's point of view, it should really be a self-contained proof. We don't really want additional entities like bridges doing this work on behalf of dApp developers. So we really want a self-contained proof. And when you look at this proof, you should be convinced that this is a genuine state signed off by the latest address book on a Hedera or a Hiro network. So if you go deeper, what a TSS proof is proving is two things. One, that a threshold, let's say half of the network address book by weight has signed off on the block. And two, that the address book in question is actually a genuine address book. That it's a descendant of the address book that you had at Genesis. And along the way, you could have several transitions. You could be adding nodes, removing nodes, changing their weights. And regardless of how you got there, you know that this is a genuine address book, and you can trust any proof verified with respect to that. So those two things coming together forms a valid TSS proof. Now, to build TSS, we had to actually come up with a lot of cryptography. We had to invent some stuff. We had to also build on top of stuff that has recently people been working on in the space of snarks, zero-knowledge proofs, threshold, and distributed cryptography. And really what made it challenging is the two things that I spoke about. Supporting weights. A lot of distributed cryptography or threshold crypto systems never really considered the supporting weights when it comes to modeling trust. The other thing is, as I mentioned, the proof here has to be self-verifiable. As in, just looking at the proof with respect to something, a small verification key that we establish at Genesis. And in our case, we have a cryptographic digest at the time of Genesis, which we call a ledger ID. Just using that ledger ID, you should be able to verify any TSS proof at any point in time. Meeting both of these guarantees together turned out to be quite a challenge. and I'll just describe very briefly what entails here. So just before I go on to talk about how we built our TSS, I just want to summarize the requirements that we have. So we want a short proof. In our case, it's 2 to 3 kilobytes, not too large. And we want it to be verifiable against a small cryptographic digest that we established at Genesis called the ledger ID. And any TSS proof has to be verifiable with respect to that. And our ledger ID is something like 256 bits, so not too large again. And it doesn't grow no matter how the network evolves. The two main components in TSS, as Mark and Nana pointed out, is hints and wraps. So I'll just quickly mention what those two are. So hints is a threshold signature scheme. Its job is one thing. It's to prove that a threshold, a half, for example, a half of the address book has signed off on a given state. And it's built on something called threshold signatures. A threshold signature is a cryptographic protocol which allows a it's a cryptographic protocol which a set of nodes can participate in, and it outputs a valid signature where at least a threshold number of participants must have participated to create that. That means less than the threshold number of participants, even if they act maliciously, they cannot create an invalid signature. And what makes threshold signatures interesting or non-trivial to build is that they must also be, they must support this feature called aggregation. No matter how large your network is or what your threshold is, your signature has to be a fixed size. And that's what really makes threshold signatures interesting to use and also hard to build. And if you notice, I'm using the term threshold number, because in cryptography, until now, we didn't have a way to support weights when it comes to threshold signing. So HINTS is the first threshold signing algorithm to support weights natively. It's a protocol that we developed in collaboration with several academic folks as well. It's pretty convenient to use. It produces a fixed signature, about a kilobyte or so. And the signing process is also pretty convenient. To sign off every block, every node publishes a small signature that gets aggregated together to produce this aggregate signature that's only a kilobyte in size. Now, the other component here is, how do we trust the fact that this hint signature is valid? Well, the hint signature is verified with respect to an address book, but we have no way of knowing that the address book is safe to trust. And that's where the other proof system, wraps, comes in. TSS contains both the hints and the wraps proof. Wraps' job is to prove that the latest address book is a descendant of the Genesis address book. And the way we do that is, whenever we change our address book, and it could be changing because we're adding or removing nodes, or it could be changing weights, whenever we do that, we have the members of the existing address book sign off on the next address book. So what you have is basically a chain of sets of signatures going all the way back to Genesis. And of course, if you take all of those signatures and you give it to a verifier, that's technically a self-contained proof. If a verifier looks at all of these signatures, that verifier is convinced it's a valid address book. But that's not so convenient. If you recall, our goal is to have fixed size proofs. And that's where we use zero-knowledge proofs. So I'm sure a lot of us here have played with zero-knowledge proofs or snarks, but let me quickly summarize what those are. It's a cryptographic protocol between a prover and a verifier, where a prover takes a computation starting from some state and a set of inputs, and it proves to a verifier that you got to a final state. And this could be any computation. It could be EVM computation, proving that a set of transactions have been applied correctly to state. Or it could be verifying signatures. Verifying signatures is another type of computation. Whatever your computation is, a prover can prove to the verifier that it is a valid computation. In our case, what we can do is we can feed the chain of signatures that I spoke about. A prover can prove to a verifier that there does exist a chain of signatures going back to Genesis. And in our case, a prover would be, let's say, the net consensus nodes constructing the TSS proofs. And the verifier could be a dApp developer or mirror nodes or what have you. So are we done? Well, almost. A verifier is happy. A verifier just looks at a tiny proof. And by the way, in zero-knowledge proofs, we typically have a property called succinctness. That's the S in snarks. That guarantees that a verifier with a tiny amount of work can verify a proof attesting to any length computation. So one would think that we're almost done here, but not quite, because as you can imagine, every day, whenever we rotate our address book, we have more and more signatures. So we can only do this for maybe a handful of days before we really start to struggle. So that's where the proof system in wraps, it makes use of a concept called recursive snarks. Now, think of back to mathematical induction from high school. It works basically the same way. If I gave you a recursive proof for yesterday's address book, and I gave you a set of signatures from yesterday's address book blessing today's address book, The two together should be enough to construct a new recursive proof that is blessing today's address book. And now the prover's job is not growing with time. Every day, or whenever we choose to rotate our address books, all it's doing is taking as input the previous recursive proof and the next set of signatures, and it gets a new proof. And that's how we keep things succinct. That's how we make sure TSS proofs are always a constant size, in our case, 2 to 3 kilobytes. It is always verified with respect to the ledger ID, which is a small 256-bit hash of, and in this case, it's the hash of the Genesis address book. And that's it. Yeah, the two things, the hints and wraps, comes together to form TSS. And yeah, we're excited about it. And of course, we're not done yet. We're now looking at how to make everything post-quantum. But post-quantum transition is a pretty large agenda for us. So I'm going to let Leemon talk more about that.
Yeah, so this is really exciting. We are using a kind of threshold signature that other people don't have. And without that, for a long time, we thought we weren't going to have what you invented. We thought that we were going to have to say we're proof of stake. Each node has an amount of stake that is any number of tiny bars or H bars, but we have to round it to a number from 1 to 5. That's what we thought for a long time we'd have to do, which is really ugly. It's not exactly proof of stake, it's rounded proof of stake. And you found a way of solving that, and it's totally solved now. Any number of H bars can be staked, and that is your weight in the voting. And you did it. And in 2018, we said we're going to do state proofs that would have a chain of address books, and the more years our network runs, the bigger your state proofs get. And you crunched it down to a finite size, and it will never change. It's a constant size, no matter how long. I love this. So that's what he's done with that. Post-quantum is also an important thing. Quantum computers are not going to be here this year. The world's experts don't think we're going to have giant quantum computers that can crack cryptography this year. We have them, but we don't think they're going to be big enough to do cryptography, and low enough error rates, and enough logical bits, and all that stuff, qubits, all that stuff. So what we think is that it's going to be years before we have quantum computers that can break cryptography, but there's a good chance that will happen eventually. So a lot of experts say, yeah, maybe 10 years from now we will have a quantum computer that is cryptographically relevant that could break all of our cryptography. That's bad. What about us in Hedera? Can we become post-quantum, be safe against giant quantum computers in less than the 10 years that we have maybe before we're really in danger? And yes. So we do 4 things in our cryptography. We do hashes, we do encryption, we do key agreement, and we do digital signatures. Of the 4 things that we do that are cryptographic, 2 of them are already post-quantum. Our hashes are 384 bits. We are totally secure, as far as all the experts on Earth believe. And our encryption is AES 256. Everyone on Earth thinks that those are secure. Our key agreement, this is how when our computers are talking to each other, the mainnet nodes, they encrypt all the traffic going back and forth, and they have to agree on the key to use to encrypt it. Really, we don't actually need that. We'd be secure even without it. We could just send it in the clear. But it's nice to be able to encrypt it. It's one more layer of security. And for that, we need key agreement. We use TLS. When you go to a secure website, that's what keeps you secret. You go to HTTPS instead of HTTP. You go into a secure website, a little lock appears on your browser or whatever. That is TLS. And we use that between our mainnet nodes when they're talking to each other. And right now, the encryption part of it is fine, but the key agreement part of it could be broken someday when we have big quantum computers. So 10 years from now, maybe that would be broken. Not a big deal, don't really need it for security, but it's kind of nice. And the same thing when somebody submits a transaction to the network. You can do it unencrypted, or you can use TLS, and that would be breakable. Now again, no one's going to steal your money based on it, but maybe it makes front-running easier if someone could break it. So it'd be good to have that be post-quantum. Good news, NIST, this is the government body that does these things, has had a contest for almost 10 years. It started 10 years ago this December, so we're almost up to the 10-year point. And they had a contest where the very top cryptographers all around the world tried to find algorithms that would survive the quantum computer revolution when it comes. And what they did is they finally agreed on algorithms for doing this. They agreed on a way of doing key agreement. ML-Kim, it's called Kyber, like Kyber crystals that make your lightsaber in Star Wars work. And it turns red if you turn to the dark side. That is what they named it, and that is now the standard. And people are putting this into TLS. TLS 1.3 is getting a new version that has this. And people are doing this. Apple just added this in November or December to iOS. For Java, OpenJDK says they're going to roll it out this summer. So this is slowly rolling out. When our libraries support it, we will change that one line of code that turns it on, and then we will have post-quantum key agreement. And our TLS will be post-quantum, and giant quantum computers someday will be unable to break it. And again, we don't really need it for security, but I like the belt and suspenders, the extra layer of security, and maybe it helps you a little bit with front running. We will have that. And I'm expecting that this year. I mean, that's just, as I said, OpenJDK is rolling it out this summer. Apple just rolled it out a couple months ago. I think that the libraries we rely on will have the latest version of TLS sometime this year, and we'll turn it on. Easy to do, no real cost, doesn't slow things down. It's just good across the board. And then there's signatures, digital signatures. This is the big thing. For post-quantum, you need this, because when you do a transaction and you digitally sign, yes, I want to move tokens out of my account, if a big quantum computer could break that, then a big quantum computer could let the attacker steal everything you have. That would be somewhat bad. This is the big threat that every blockchain is worried about, is digital signatures. This is the real danger. We use it internally and externally. Internally, we use this for the Hashgraph. An event is a node, a mainnet node, creates an event and digitally signs it. And these events form the Hashgraph. It's what does consensus. You could cheat on consensus if you could forge these signatures. That's bad. And then we use them for our history. The record stream has lists of signatures. And so internally, we rely on signatures that can't be broken, can't be forged. Externally, as I said, every time you sign a transaction to move stuff out of your account, you're digitally signing it. If an attacker could fake your signature, they could steal everything from every account on the whole network, in every blockchain. Those are vulnerable. Right now, in Happy, in the Hedera API or the Hyro API, we have a message called key, capital K-E-Y. This is the key that you put on your account when you create an account. And it can be ED 25519. It can be ETHDSA. It can be a smart contract acting like a key. It can be a list of keys that 3 out of 5 are needed to sign, 15 layers deep. We have this list of different keys you can use, and they are not post-quantum. ED 25519 will be broken someday if we ever get giant quantum computers. ETHDSA will be broken someday if we ever get giant quantum computers. So 10 years from now, there's a good chance, not necessarily true, but a good chance those will be broken 10 years from now. So we need to fix this. What do? We're going to use one of the ones that won the contest. So Sphinx won the contest, and a digital signature is tens of kilobytes. Yeah, that's the non-starter. Also, dilithium crystals won the contest. Crystals dilithium from Star Trek, using the warp drive. That one won the contest, but it's over 2 kilobytes for the high security signatures. That's really inconvenient. If we had to, we would do it. But Falcon won the contest. It's only 1 kilobyte. Yeah, it's still bad, but it's only half as bad. We'll use Falcon. Now, the Falcon standard hasn't been published yet. It won the contest, but it hasn't been published yet. I expect it to be published any day now. We really thought it'd be by December. They said it'd be done by the end of 2025. When this draft standard is published, we will immediately use it for our internal signing of the events. It's a draft standard. Maybe it's not secure, but we'll just sign it both ways, the new way and the old way. So if you break the new way, who cares? We still have the old way protecting us. And if someday somebody builds a quantum computer, well, the old way is broken, but we have the new way to protect us. So we will do this immediately. It isn't something we have to support forever. If the standard changes by the time it's final, we'll just use it for a little while. And so we will have that. And then a year from now, the final will come out, and we'll just use the final. We won't even do the old signatures. For external, we will change the accounts to allow a new key type of Falcon. As soon as the final one comes out, about a year from now, we will allow that for users. Then we would encourage all of you, if you are building wallets, to nag your users and say, hey, you haven't upgraded to the new keys yet. Push this button, and you will upgrade to the new keys. You don't need a new account. It just rotates keys. It's great. And you don't even have to have a new 24 words. You're still protected by your old 24 words. It'll be very painless. So if you are developing software that manages accounts, please do that. The final version should come out a year from now, and we will implement it, and it will be something users can then upgrade. I'm excited about this, and then we'll be completely post-quantum. I wish I could talk to you more. What you're doing is exciting. What you guys are doing is exciting, and I look forward to talking to you in the future. Thank you.
All right. Thank you, Leemon and Rohit. That was absolutely amazing. Fortunately for all of us, there's going to be more of this great type of conversations at HederaCon that's happening in Miami on May 4th. So right now, you can scan this QR code, go and register today, and I look forward to seeing many and all of you there at HederaCon. All right, so right now, we're in the lunch break, so the stations are going to be open. This is a great time to network, complete that scavenger hunt, collect some points, and we'll meet back here at 1:45 p.m. local to start our hands-on workshops. Enjoy the lunch.
taking the world you see. They'll be calling me, they'll be calling me royalty. Best to give me loyalty, 'cause I'm taking the world you see. They'll be calling me, they'll be calling me royalty.
Let the darkness shine. some smoke. Breathe me in and let me go. Sink to your heart to find you. Open up your eyes till you're blinded by the lies, so you can see what you do. Restless every time we start locking as lost control. It's paradise with honesty, but in the dead of the night, teardrops on the floor. The pain is over, feel the darkness take control.
Like a Hellcat.
So you wanna go to war with me? You're talking like you think you're royalty. You think that I'm afraid, but I don't break. I heard you question my stability. You think I'll fall just like a guillotine, but I am here to stay. Won't look away. The storm is coming, so you better start running. No, you can't control, feel it in my bones. I'm coming for the, coming for the. I'm coming for the throne. For the throne. So you wanna be my enemy? You should've known I'd never kiss the rain. Ice runs in my veins, won't play it safe. I don't belong with your nobility. Who died and made you king of anything? You think that I'm insane? It's your mistake. Kingdoms rise and fall. I've come to take it all. I'll take it. I've come to take it. Kingdoms rise and fall. I've come to take it all. I'll take it all. control. Feel it in my bones. I'm coming for the, coming for the. I'm coming for the throne. I'm coming for the throne.
Got a monster inside of me, you better watch out. If you ignite me, a road ahead of full prophecy to be the greatest beast the world has ever seen. I feed him every day, leave the bones clean. I feed him all the hate and he grows me, and he gets claws real big, pissed off quick. And if you cross him, you might drop dead. Metaphorically, of course, settling the score, never getting bored, loves the blood and gore. Always wanting more freedom from the source. They don't really understand until they feel the force departed. If you start shit, you'll be heartless in the darkness. Torn apart quick, you left scars ripped, you'll be chewed up and discarded. And this world ain't right, won't accept it. Negative energy, I expect it. Once it's in your mind, it's infectious. So fight for your life and reject it. You better give me space, I'm protective. My adrenaline spikes when I'm threatened. And if you stay in my way, I'm aggressive. Cause when there's no exit, I'll kill when I'm desperate. Pressure, it's stormy weather, lightning, thunder, pouring weather. Yo, I'm a go-getter, try to do it like me, but I do it better. I got a mind that's clever, the beast inside is competitive as ever. I'm conscious, my subconscious, an accomplice to me. I promise the darkness, I can honest believe. But don't cross me, I might lose control of the lost beast. He's locked away inside with the key controlled by fight or flight. And this world ain't right, won't accept it. Negative energy, I expect it. Once it's in your mind, it's infectious. So fight for your life and reject it. You better give me space, I'm protective. My adrenaline spikes when I'm threatened. And if you stay in my way, I'm aggressive. Cause when there's no exit, I'll kill when I'm desperate.
Big way when I'm walking, pray when I'm talking this to you. Fight for my attention, for your ascension, you must prove. 'Cause if you can find it, you don't confine it, you let it move. Make way for the genie, scream for the dream, may coming through. Have you ever played with a queen? I can show you what I mean. I can make you feel free. I got you in another league. Can you meet me on my level? Oh, baby, is you right over? Can you battle with the devil? Oh, baby, is the game over? I want your devotion, all your emotions in my hand. I want your obsession, every affection, full man. And if you define me, you won't survive me, you'll be there. 'Cause I am the giant, I am the diamond, not a man. Have you ever played with a queen? I can show you what I mean. I can make you feel free. I got you in another league. Can you meet me on my level? Oh, baby, is you reign over? Can you battle with the devil? Oh, baby, is the game over?
Hedera DevDay will resume in 15 minutes. Please find your seats, grab a coffee, and get ready for some more building.
Wake up to the sound of thunder, like a whisper in my ear. Are you gonna wait forever? I can see the stars reflecting, empty tires made of steel. Everything but you is fading. I see you lie. Take me away from me, beyond the stratosphere. I'm burning up. You got me falling free into eternity. When you tear up my horizon. I've been used to breathing darkness. The hunger never disappears. Cause the memories have turned to ashes. Oh, still I'm floating but I won't surrender to the tide inside of me. Drowning in the endless silence, but I'm who I'm meant to be. I see you lie. Take me away from me, beyond the stratosphere. I'm burning up. You got me falling free into eternity. I'm walking alone, the streets are empty. The only thing I can see is my own silhouette. I'm getting stronger, step by step. The clock is ticking, but there's no time for regrets. I've been flying from town to town, from London to Taiwan. I've been all around the globe, trying to protect your soul. We are heroes tonight. We will fly above the sky. We are heroes tonight. Yeah. We are heroes tonight. We will fly above the sky. We are heroes tonight.
Hedera DevDay will resume in 10 minutes. Be sure to make your way back to the main stage and find your seats.
You to hear and don't show any fear. I've been flying from town to town, from London to Taiwan. I've been all around the globe, trying to protect your to protect your soul. After my silver soul, can you dig any deeper now? I gave you all I own, put you on this golden throne, but I'm a little stronger now. You cashed in on my promises. You know I'm too generous. Now I've learned to never help you out. 'Cause I'm done cleaning up your mess. Found myself in my regrets. I've become a little stronger now. A little stronger now. You cashed in on my promises. You know I'm too generous. Now I've learned to never help you out. 'Cause I'm done cleaning up your mess. Found myself in my regrets. I've become a little stronger now. 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 You cashed in on my promises. You know I'm too generous. Now I've learned to never help you out. 'Cause I'm done cleaning up your mess. Found myself in my regrets. I've become a little stronger now. A little stronger now.
Hedera DevDay will resume in 5 minutes. Please take your seats, settle in, and get ready for more building.
My heart rages around like an ocean in my head, because there are so many things that I left unsaid.
distance, but I know that it's not reality.
Hedera DevDay is about to resume. Please take your seats. Please join me in welcoming back to the stage RMC, Hashgraph's Head of Developer Relations, Ed Marquez.
All right, everyone, welcome back. We hope you're enjoying the event, you're enjoying the day, and you had a great lunch. Now, let's dive deep into a workshop and kick off these technical and hands-on sessions. This is going to be a workshop about self-executing smart contracts. So no off-chain bots, no off-chain schedulers, just keeping it all on-chain with self-executing contracts. So for that, join me in welcoming to the stage Kieran Pakai and Michael Bennett.
Hey everyone, thanks for coming.
Hi everyone, I'm Kieran, this is Michael. We're developer advocates. Before I say anything, I want to demonstrate, and action speaks louder than words, or so I've been told, so I'm just going to demonstrate what we're going to be building today. So here I have a contract, a simple contract. Again, we can look at the code later, but for now, what I'll do is I'm going to pay special attention to this contract address, ends with 37E. What we're going to do, I'm going to go to calls and see all these different transactions. You see, we have these transactions occurring every 15 seconds or so, and we're going to see one in a little bit here. But if we go to Events tab, we see, okay, every time, every transaction is printing hello Hedera every 15 seconds. And if we look at any one of the transaction, let's dive into it a little bit here, right? Let me open another one. Okay, so here, well, let's just go to the events. That's fine. So you might be wondering, well, why are these events being printed every 15 seconds? Trust me, I don't have a person somewhere executing these transactions. These are actually happening in real time. What's happening is every 15 seconds, the protocol itself is waking up our smart contract and calling a specific function and then printing the message, in this case, emitting an event. And you might be wondering, well, how is this happening? Right? We don't have any off-chain infrastructure, off-chain bot server. There's no Chainlink Keeper, Gelato, like none of this. It's all happening on-chain. It's the protocol doing it. And today we're going to be deploying the exact same contract. We're going to do it live, and hopefully all of you can also do it live with me, because it's quite easy to get started here. Let me go back to slides. All right. So the agenda for today, first I showed the cron job that was happening on chain. These transactions were happening every 15 seconds automatically, and we're going to talk about what exactly enables that on something like Hedera. Like you don't see this on other EVM chains like Ethereum or Base or anything else. You need to use this off-chain infrastructure. And we're going to talk about Hedera scheduled service. And then after that, we have a hands-on exercise. We're going to be deploying the contract. And then we're going to talk about some use cases that this specific scheduled service enables. And then some of the next steps. All right, first of all, when we talk about any kind of smart contracts, they all have an automation problem, right? Smart contracts, like we've heard this term smart contracts since 2015, but can we really say they are smart in the traditional sense? Because if you think about it, a smart contract, all it does, it sits on chain, it doesn't do anything by itself. Someone manually has to poke at it by sending a transaction, and then it executes it, right? There's no like, if the transaction is not executed, if the transaction is not triggered, then it's not executed. It's as simple as that. And it's almost like when you have all these kind of things happening, like some of the times when you're dealing with time-based capabilities you want to introduce on your contracts, you have to rely on some off-chain infrastructure. We talked about Chainlink Keepers, and you may even have your own cron job running somewhere that is executing these transactions every so often, every day, every week, whatever. But when we're dealing with time-based capability, right, as an example, right, if you want to rebalance a vault in a DeFi setting every hour, if you want to have a recurring payment once every 7 days for the next month or so, or for the next year, or if you have like a governance proposal that needs to be executed without you manually triggering the execution, well, it's just not possible because it's not possible at the protocol level. And that's most of the problems that we see on other EVM chains. So how do they solve it today? So what happens is you have some kind of network, like a Gelato network or OpenZetLim Defender, or you might have your own custom bot server somewhere to automate this entire process. And thousands of protocols have been using this for a long time, and it works, right? It works. But the problem is there is still some centralization risk that comes along with it, because you're still having to trust that other third party to execute your transaction at a specific point in time. If something were to go wrong, at 3 a.m. and your DeFi vault doesn't get rebalanced, well, your users might get liquidated for no reason, right? And there's also additional cost. In addition to paying for the gas, you're also paying some sort of recurring fees to have this off-chain service. And there's also some trust assumptions. You have to trust this centralized party or out there somewhere to do the work that you want it to do. And then there's also the infrastructure overhead. Someone needs to manage that server. It's just a lot of cost associated with it, right? It works, it solves the problem, but you're still trusting someone or something to call your contract, and you're paying for it. So how do we solve that on Hedera? And I'll let Michael talk about Hedera scheduled service.
Yeah, so let's understand a little bit more about HSS and how it works. So it's a native Hedera service that allows transactions to be scheduled for future execution at the protocol level. There's no other third party involved in it, as Kieran had mentioned earlier. We schedule a transaction, Hedera stores that call data, and then at some point in the future, we have automatic execution of that wrapped transaction from the HSS, which is all really cool. But we could also do this from smart contracts as well. So we can now have smart contracts schedule themselves or other smart contracts. And that's done via HIP 1215. So HIP 1215 is a bit of a game changer for generalized scheduled contract calls, as the title states. It allows you, inside your contract, to make a schedule call to 16B. We kind of mentioned earlier was a precompile that's been added into the EVM network to allow us to talk to native services under the hood. The HSS will store the transaction that you want to call in the future, along with an expiry date and some other metadata. When that time happens in the future, the consensus node picks up the transaction from the HSS and then executes it on the consensus node. So this is all happening on the network itself. There is no third party involved. What it allows us to do, essentially, is to have on-chain cron jobs, self-perpetuating contract logic, which allows, if a contract does something and it's a successful transaction, it can then decide to call itself again and recommit, which is pretty cool. Truly, you're going to get smart contracts at that point. We get fully autonomous smart contracts and zero off-chain infrastructure, which is really cool. Gives you, less technology to manage as you go along. So, as Kieran had alluded to before, there's ways to solve this in other blockchains, and it has been solved. We have keepers, the networks, and your own servers to do this kind of work. It has a lot of external automation. You need to know DevOps. You might need to know security. You have to do a lot of key management that's kind of problematic if you don't get it right. Additional costs and multiple points of failure. Whereas the Hedera solution is a lot more elegant and simple. You have a smart contract. It's funded. It can schedule calls. They auto-execute in the future via the HSS, and it all happens inside the consensus layer. It's native. It's built in, and there's no external dependencies. Okay, if you're doing the scavenger hunt, you know what you need to do. All good? Okay, so back to Kieran, and he's going to show us now a kind of hands-on exercise on how to actually use this technology. Thanks.
Thanks, Michael. All right, thanks for the introduction to scheduled service. For the next part of the presentation, I'm going to be demoing deploying the contract. We're going to interact with the contract. We're going to look at it on the Explorer, how it looks like. When you're talking about a contract that schedules itself in the future, sort of like I try to use an analogy, it's almost like if a runner were in a relay race, the way that scheduled service works is a runner passes the baton to himself in the future across time. That's how I like to imagine it. That's basically what happens here. So I'm going to talk about the pattern to be aware of. And again, this is just a pattern, right? But it's super straightforward to understand how the mechanics work if you understand how the whole scheduling system works on Hedera. So the first thing that we need to worry about is, there's three different processes, three different stages as part of the pattern. The first is the initialization function, right? This is the function which you initially call to get the schedule started, and it will handle, things like, schedule, keep repeating this schedule like 15 seconds from now, and I want you to emit an event. I want you to do something, balance, pay, whatever it is. That is part of this function, this first entry point into the scheduled service. And what's going to happen is, and then the second is the worker function. The worker function is where the magic happens. Because what happens is when those 15 seconds or 30 seconds, however much time you have passed in on your cron job, passes, the consensus node, the network itself, wakes up your smart contract and then calls your smart contract with the function, with the call data that you gave it as part of the initialization function. So let me back up. So if you have on this worker function, if you may have a function that just emits an event that says, hello, Hedera, every 15 seconds. So what happens is it emits that event, and then at the end, right before it ends, it basically schedules its next execution, next execution 15 seconds from now. So, and then the loop continues forever and ever, or until your contract runs out of HBAR. So if you have a lot of HBAR in your contract, you do need to be aware of. You have this scheduler service running, and it's just going to keep running until you exhaust it. Or coming back to the third stage, which is the function for stopping, because you want your scheduler to stop. Maybe like something happened, you just want to stop it midway. You can always restart it, but you also probably need to have a stop function to stop it midway. If you're running out of HBAR, you want to replenish that. Again, like if you run out of HBAR in the contract, it will just fail and it will stop the loop. So you need to restart the scheduler, but that's the pattern. All right, let's go back to the demo. I am going to open up this guide, and this should be part of the prerequisites. If not, it should be in the same repository that we're using here. Just to reiterate, it is on Hedera -dev DevDay tutorial hello scheduled world. You can go to docs and then guide if you want to follow along with the guide. But just to keep things simple, what I'm going to do is I'm going to walk through this guide, and I'm going to show you how exactly you can deploy this contract and then interact with it and schedule and do all kinds of crazy stuff. All right, so first thing you need to have is, obviously, you need to have some testnet HBAR. So if you haven't, go to portal.hedera.com and then get some HBAR, your hex-encoded private key. Start with 0x. All right, this first thing we're going to do is we're just going to create a directory first, so we can just start everything fresh. So I'm in this directory. All right, let me make it bigger. I'm just going to copy paste. So all I'm doing is creating the directory. I change it to the directory. What I'm going to do is I'm going to initialize this project with Foundry, with Forge. So it's going to initialize, we look here. You see the live directory, that's all the dependencies. And then you have the test, and then it comes with the default counter contract and test. So I'm just going to remove all that first. Let me just open this on VS Code. There we go. Just for the sake of it, I'm going to open this also in the same one. So, all right. Just to make things simpler, I'm just going to do everything on the VS Code here, so it's easier to follow along. All right. So the first thing we're going to do is we initialize our directory with Forge. That's all dandy. I'm just going to remove these files that I don't need, because I don't really need them. Again, just to make things simpler, instead of typing all this, I'm just going to copy paste. And I'll explain a little bit about all the code that I'm copying pasting. So for now, let's just copy paste. So all we're doing is we're setting our profile on Foundry. So we're going to have an environment variable later, which is going to define our RPC URL, and then this just comes with it. The remappings is more there for, because usually what happens is when you install a particular library dependency, it's under some, in this case, it's lib Hedera smart contracts. And in order to make things simpler, I want to be able to import on my contract with something like add hashgraph/smart contracts. So that's why we have the remappings here. But that's all. That's all we need for the foundry.toml file. Next, we're going to create our environment file. I already have an environment file, so I'm just going to copy that over on this directory. But you'll probably need to substitute this to your own hex-encoded private key. Next thing we're going to do is we're going to load our environment variables locally, so we can play around with it through Foundry, so through Forge. All right, so next what we're going to do is we're going to install our smart contracts, system smart contract library directly in Foundry, so that we can utilize the Hedera schedule service precompile, and that exposes a lot of the things that makes our whole smart contract self-executable, repeatable in a cron job manner. So let me just copy paste this. So this is going to install this locally. May take some time. Next, let me talk a little bit about this. So what we have here, and this is one of the key functions, and we'll show this in the code later, but this is the core function that is going to be rescheduling. So here on the address, this is the contract that you're asking the protocol to call. So in our case, because we have this cron job that's going to execute its own function in the future, the 2 will be the address of the smart contract itself. So it's sort of the relay race analogy that I told about earlier. The expiry second is when you want to have the network call your function 15 seconds, 30 seconds, a week from now, 2 weeks from now, whatever it is, right? And the gas limit, you probably want this to be enough that whenever the smart contract calls itself in the future, you have enough gas Otherwise, it's going to revert, so you don't want that happening. And we're going to see that. We're going to see how to set that later. And then value, usually for this use case today, it's 0. But if your function requires some kind of value, sending hbar, you can do that. Call data is where majority of the encoding happens. So in our case, we're going to have a function that's just going to emit an event and then schedule itself in the future. So all of that is going to be encoded, and then we're going to pass it in to this schedule call function. All right, so let me copy this first, and I'll explain a little bit about the structure of this contract. There it is. All right, let me create a directory, file called hello scheduled world.sol, and then explain a little bit about this here. Make it bigger. All right. So here, let me just do this. Don't need to do that, but let's just ignore that. We don't want the linter complaining. All right, so here, first, we are importing Hedera schedule service from our system contract library. This is the full path here, but again, you can feel free to check out, you can check out more about all the functionalities that Hedera schedule service exposes. One of them is the schedule call that we talked about, but there are some other functions as well, you're able to have a function, we don't have that in this demo, but in the second demo, where you're able to check exactly the time slot that is going to be open to execute your call in the future. That way, whenever, you can know exactly ahead of time that your function is going to be executed at that particular time. So here I'm setting the gas limit to be 2 million. That's fine for this case because, as we know on Hedera, as of recently, no matter how much gas limit you send in, it will only consume the gas that it actually uses. So you're not going to be charged for 80% like you used to before. So that's good. It works for this. We have our constructor, and then we have our receive function. The reason is, someone has to pay for the scheduled transaction, and it's the contract paying for that. So you need this receive function so that you can send, and also constructor to be payable. So you can send some hbar to your contract address, and then the network, when the network calls your contract later on, 15 seconds, 30 seconds, it will just reduce that amount from your contract balance. So this is the meat of the project. So this is the initialization function that I talked about earlier, which is the entry point, right? We have the message, hello Hedera earlier in our demo interval, let's say 15 seconds, but you can really go far in the future. And then this is an internal variable that is going to keep track of whether the scheduled current cron job is active. If it's false, then it's not going to execute. So, and then we have this schedule function. It's an internal function. All it's doing is, as I was talking about earlier, we have this print message function. Let's just look at that. So this is our worker function I talked about earlier on our pattern. So all it's doing is it's checking, okay, is active? Is the cron job running? Am I supposed to run it? Okay, if it's active, then we go ahead. And then it's going to emit an event with the message that we passed in initially. And then it also includes the timestamp. So we know we can check it later when it got executed. And then the last thing that it does, remember, it needs to be able to schedule its own future call. So it just calls schedule again. So we're re-entering here to basically encode all the message, all the data that print message requires, and then we're passing this data in to the schedule call function. Remember, I talked about schedule call function here. It takes 2 expiry second, gas limit, value, and call data. That's exactly what it's taking. So here we're passing our own contract. You can pass in another contract, that's fine. And we have the time, which is whatever we set it. Gas limit, we're passing the gas limit. 0 in this case, but it may be different for your case. Data is the actual data of the function that we're trying to execute every so often. And then last but not least, if it fails, then it's going to say schedule failed, blah, blah, blah. And that's it. It is under 50 lines of code. And this is all you need to have a cron job running on chain. So the smart contract, the protocol wakes up the smart contract executes its own logic, and then the last thing it does is reschedule itself whatever time in the future that you set it. That's all it's doing, right? So let's go ahead and, let me come back here. Whoop. Let's go ahead and build our project. So Forge build. It's going to compile. So here I'm using Forge to basically deploy the contract. If you're not familiar with Forge, here all I'm saying is, OK, Forge, create or deploy this contract that is on source hello scheduled world.sol. That's the contract name. And then we're passing our RPC URL, which is set in the environment variable. And then let me just do this just in case. And then we're passing the private key because you're signing with your account. And then I'm going to send some Ether. In this case, it would be HBAR, because that's just the syntax that Forge has. So Ether, just remember that this is just saying 10 HBAR. And then broadcast is just used to broadcast the transaction. So let me just copy this code and deploy this contract. All right, so we have our deployer. This is our account that I'm using to deploy. This is where it got deployed. And then this is a transaction hash. We can check this really quickly here. So if I go here, here's our contract. All right, well, I can't see any bytecode here, actual source code. That's because the contract isn't verified. We're going to solve that pretty quickly here. So first thing we want to do is, and we're going to use this later, so I probably want to set this variable, contract address equals this. And then, again, this is an optional step, but if we want to see what's going on, like if we want to trace all the events, like all the data, we probably want to verify it. So this is a helper script. It's all in the documentation, but there's a helper script that generates a metadata.json file that you can just feed into Hashcan, and it works with Foundry and Hardhat both. And it's a really easy way to generate the entire metadata. It works for multiple contracts at the same time. Like, it works for all use cases. So I'm just going to copy this, and all it's doing is making this verification, the metadata generation script available so to be executed. And then I'm going to generate this. All right, now you see here, this is the metadata JSON file. So I'm going to do hello metadata. Let's do downloads. All right, I'm going to quickly verify this. All right. There it is. Got it verified quickly. Now we can look at the source code, ABI, source code here. All right, now we're ready to execute our function. So next step is, so we're using Castor. We're dealing with Foundry today, so we're just going to be using all Foundry and Forge-related commands. But all this is doing is it's calling our initialization function, like scheduled message. We're passing in hello Hedera every 15 seconds. We're passing in our RPC URL, and then the private key, right? So let's go ahead and execute that. All right, got executed. We can check the calls tab here. All right, so if we look at the trace, okay, scheduled message, it got scheduled. Let's wait a little bit here, 15 seconds, and then we'll jump back when I refresh the page. There it is. Oh, wait. Yep.
Yeah, just first one.
Okay. Let's go to trace. So this is the first call. So we see here, this is the contract address. We see here, like, this scheduled transaction got executed. Usually, these two addresses are different, right? Because someone else is calling it. But here, in this case, it's the contract for the from address, and then it's the contract itself for the to. Because the contract is calling itself with however many, and it's executing this print message. That's all it's doing. And if we look back again and again, you see here, all of these are getting executed. Again, this is my account. I'm just executing locally, but every 15 seconds, we look at the events tab. We see hello Hedera, timestamp is there. Every 15 seconds, we have a working code. we can also check something here pretty quickly. So all this is doing is checking whether the cron job is active. We're calling the isActive public function of the contract. Same thing here, like what's the message, hello Hedera, and then we can even check the interval currently. And then if you check the balance, it should go down every single time. Now it's down to 1.5 hbar. That's probably because it got executed and you spent all that hbar already. So, and then there's also a function to stop scheduling. Let's go back here, one last thing. And here you see that the last transaction, it says, well, it failed. Why? Because insufficient pair balance, because we only sent 10 hbar, and we ran out of hbar pretty quickly because I'm executing it every 15 seconds. So you can see here, all of these are scheduled transactions that got executed. Eventually, it ran out of hbar, and then it reverted. Now, if you wanted to reschedule it, all you have to do is top off this contract address, and then call the start scheduling function again, and then you can start the whole process one more time. But we're not going to do that. All right, let's see what else. I think that's part of the demo. Let's jump back to, oh yeah, one more thing. So I'm just going to quickly show a demo here. This is an entirely different contract. This is an ERC20 contract that has an airdrop functionality. So you can set it so that every 20 seconds, I'm going to mint X amount of tokens, and then I'm going to use the pseudo-random number generator precompile to basically randomize and retrieve whatever address that is part of the registered list. And then it's going to mint it and then send the ERC20 token to that. And you can set it, you can look at the code later, but these are the kind of things that is possible, right? Like I'll quickly go ahead and execute this so we can see this in action. Where is it? All right, we need to first register for airdrop. So let me go ahead and register. All right, asking for MetaMask. I'm going to choose a different account after this. So we have two accounts. Just want to make sure I have the correct one. All right, so I'm going to register it one more time. All we're doing is registering for the airdrop. So we have two addresses, so we can quickly check it. Right here, get recipients, we have two addresses. And then we can see, okay, let's start the schedule here, start the airdrop. It's default values that I have set here, but let me do this every 15 seconds so we can quickly see it. Max 5 drops is after 5 times, it's going to basically stop. So these are the kind of logic that you can have. And I have an optional message. So let me just start the airdrop so we can see it in action. Who gets the airdrop? All right. Let's go ahead and look over here. Oh, I should go to my other wallet, actually. Where is it? 5. Because I tried to call it from my other account that does not have access, because I'm going to show you something. If we look at the code, we are using ownable, and only the owner can start the airdrop right here, only owner. Let me go ahead and call it one more time. Start airdrop. We're just going to do 20 seconds. All right. That should be successful. There we go. All right, let's wait 15 seconds. It should go pretty quickly here. All right, let me refresh the page. There it is. Oh, wait, no. Is that the one? Yep. Yes, that is the one. So from to is the same, and we're calling it called execute airdrop. Let me go back and check who actually got the. Well, let me just check my own. Okay, this address got whatever, 303, I can't make the number, tokens airdropped. But this is the idea, right? These are the kind of things that is possible with scheduled service. So let's jump back to our presentation and end it. Let me go back to slideshow. All right, we saw the scheduling pattern. One last thing I wanted to mention, this is the entire flow, right? We deploy the contract, we call schedule message, initialization, the Hedera scheduled service stores it on the network, and then after 20 seconds or whatever time you give, the network will wake the smart contract, it'll call the smart contract will call itself, and then as part of the last thing that it does, it reschedule itself sometime in the future. It's in this case 20 seconds. So it just does that forever and ever and ever. And we didn't even need any kind of off-chain infrastructure. It was all done on-chain, possible directly at the protocol level, and this is magic. All right.
Okay. Thanks, Kieran, for that demo. So obviously we saw a few different options there, from something relatively simple, emitting a message, to something a little bit more complex with airdrops. So it kind of begs the question is, like, what can you build with it? I mean, right here we've kind of had 5 kind of general ideas of where it might kind of fall into useful use cases. So security, time lock multi-sigs, or dead man switches on contracts or functionality are really good use cases. In governance, token vesting, voting deadlines, and as we also said before, auto-executing proposals that can be a really good use of the schedule service. DeFi, lots of great use cases in there. Automated liquidations, auto-compounding yield distributions. Usually that's done through some kind of do work as people transact. It kind of piggybacks on, but you don't need to do that anymore. You can have a true yield happening at a certain time. Infrastructure, oracles are a great idea for this as well, and recurring payments. Some really good use cases. And then gaming, kind of as what we had that demo there, was like, scheduled NFT reveals, random drops, kind of it adds gamification into it as well, which are kind of really good use cases that using the Hedera schedule service and the random generator kind of together to create kind of compelling, use cases. So kind of trying to sum this up. So your competitive advantage using Hedera and being a developer, you can offer true automation on-chain, lower costs for each of your transactions and any of the tools that you kind of deploy. Higher reliability. It's a protocol level guarantee. It's stored on the consensus nodes and it's executed on there. There's no third party to kind of worry about for any kind of connectivity or kind of issues. Balanced with that as well, there's other zero infrastructure costs to you. So if you have a DApp or a project or that, you don't need to worry about infrastructure in AWS or DevOps to kind of have this thing working. And then also full transparency. Everything is visible on chain, so people know when things are going to happen, and you can see that and change that as and when you need. So, okay. You've obviously seen something today, and you can continue this journey and learn more. The tutorial that we had today is available at the link there. If you want to learn more about the HIP, the specification is available on the HIP site. And then the code repository for today is available from the QR code there on GitHub as well. Okay, yeah. So, thank you all for listening to us for 40 minutes. And thanks, Kieran, for such a great demo.
We have 5 minutes, so if we have any questions, we can take them. You can see the events, you just can't make anything out of it, right? It's not verified, so it doesn't know how to decode it. So. The question was, if the contract is not verified in Hashcan, can you see all that stuff that we see on Events tab? You can, you just see the events, you can't actually decode it. Sorry? The start button? Oh, that's also one of the things, yes. The contract needs to be verified. That's why I had the first demo where I could do it from the command line if it's not verified. If it's verified, I can also use Hashcan. And in the future, as mentioned in the earlier talk, we are working on an EVM Explorer, so that should be easier to navigate.
All good?
All right. If that's it, thank you, everyone.
Thank you, everyone. Thanks for your time. Okay.
All right, that was a great workshop on self-executing smart contracts, so thank you, Kieran, thank you, Michael. Now we're gonna cover a topic that a lot of developers run into fairly quickly when it comes to on-chain data verification. We know that on-chain data integrity, on-chain verification is important, and so let's cover how you can do verification on a very large scale and of a lot of items on-chain. For that, I'm gonna welcome to the stage Ejas Merchant. So welcome, Ejas.
Ed. Thank you, Ed. Thank you for Kieran and Michael for the last presentation. So quick show of hands, who here flew in for Dev Day? Everyone fly in? Yeah, me too. Turns out that flight you took could have not happened if it wasn't for systems like we're going to talk about today. And so as you see, these are real headlines that you see. There were actually hundreds of flights grounded because of fake parts for our airplane, allegedly. And yes, there's also an eBay listing for a Boeing 737 emergency exit door. Now, can you imagine if this is what you saw on your flight the other day? And the description is pretty funny. It says, used with a small ding, fell on the ground, no big deal. But in the serious question, how do we prove that parts that airlines, automobile companies, buildings are getting are actually proven and to be real and coming from the manufacturer? How does an aviation authority verify that the serial number on that door traces back to the actual manufacturing process? So we'll dive into that today. So my name is Ejas Merchant. Welcome you guys to Designing for Scale workshop. We'll try to do a batching 1,000 records on chain, and you'll all join that with me as well. So this will be a hands-on workshop, so we'll go through some concept first and then go into the actual running it yourselves. Sounds good? Let's start. So the agenda quickly is that we'll talk about Merkle trees, we'll cover the concepts, who's already using these in the real space right now in the world, and why does this actually matter? And then we'll go through the workshop together, get our hands dirty with HCS, which is Hedera Consensus Service. We'll batch records, we'll anchor them on chain and verify them all together. And then at the end, we'll do a Q&A if needed. And if there is some bonus time remaining, I'll go through a way to run the network locally for you. So those who are interested, please stay at the end. And then if you have questions, we'll wait till the Q&A, but I'm excited to go down this with you guys. So before we begin, let's talk about what does it mean to actually batch 1,000 records on chain? Why would you even need to do this? And if you take back to our airplane example, just put your shoes in an aeronautical engineering firm. You manufacture a part that could be a door, that could be those engine parts, the cockpit parts, that could be the wheel itself. But you want to stamp it, want to prove that it's yours, and then when you ship it to Boeing or SpaceX or whoever it may be, every part of that life cycle is generating an event. You have your quality checks, your manufacturing itself, you have shipping, delivery, installation, and that's all for just one part. Now take a step back, and that could be 20 to 50 events just for one part. You add in the entire component of that plane, you're talking about thousands of parts. Now you have a really large data set here. So you want that tracked, you want it to be provable, and you also want a regulatory authority to actually be able to check it themselves. But when you think about submitting all of those transactions on chain, that becomes pretty expensive. And I think the best way of going about that is Merkle trees. So before we begin getting to that, does anyone know what a Merkle tree is? Show of hands. A few people? Great. So essentially, a Merkle tree is a hash of hashes. You start with your data. At the bottom here, you start with your data. You hash it, and you keep combining these hashes into pairs until you end up with one root. That's your single root hash. And that single root hash is, imagine, your single source of truth. So through this diagram here, you have your data. That could be anything, JSON objects, that could be transaction records, that could be airplane manufacturing parts, sensor readings, anything that you need to track, that is your data. And then each piece is hashed via SHA-256. And those hashes then become your Merkle leaves. And then moving above that, you'll hash each of those hashes. So hash 1, 2 becomes hash 12. Hashes 3 and hashes 4 become hash 3, 4. And those become your Merkle branches. And as you can see, you work your way up to the root. And then those two hashes together, hash 12 and hash 34, then are hashed again to become hash 1234. That is your Merkle root. And that is the one single 32-byte hash that represents all 4 pieces of data. Now you can imagine when there's more data, you have a few more hashes, but the end goal is the same, to get one Merkle root. And there's also one key insight, is that if anything is changed within that data, that root will completely change, and the fingerprint of this entire batch lives on that Merkle root hash. Sounds good? And just want to go through some current use cases that are out there. You see GitHub, and now GitHub is using Merkle trees for every commit. Every commit on Git is a hash that represents its parent, and that enables in integrity checking and syncing. Microsoft SQL Server uses Merkle trees for ledger tables. And the bigger one that we want to showcase today is Google Trillion. Now, Google Trillion is a open source library for transparent and cryptographically verifiable data stores on Google. As you can see, it's got about 4,000 stars, about 420 forks, and almost 1,000 projects are using this right now. And teams like Apple, Google, Cloudflare, DigiCert, and Let's Encrypt are all using this from Google Trillion. And the best thing about this is that these projects here are using this as a certificate transparency log. So every time let's say Let's Encrypt is issuing an SSL certificate, that is going into a Merkle tree. And this is kind of how you see almost the internet certificate authority kind of being honest. So when we talk about Merkle trees for supply chains, for financial auditing, we're building on a battle-tested infrastructure that the biggest tech companies in the world already rely on. And so we've already discussed a little bit about the properties of a Merkle tree, but essentially they have a binary tree of hashes. The leaves are hashes of individual records. Those branches that you saw are a hash of children concatenated together. And that single 32-byte root is representing the entire batch. But what I'd like to showcase here is this table. And I'm sure that your eyes are already gluing to what happens with the pricing between without batching and with batching. So as you can see, the last one, 100,000 records, without batching would cost $80 on HCS. Now, with batching, just like 10 records of 10, 100, 1,000, 10,000, and even 100,000, all costs less than a tenth of a cent. That's absolutely incredible. Your savings is to the right by 6 decimals. That's kind of bonkers, if you ask me. And this proof size grows logarithmically. So that's cost is staying flat. So that's the entire point here. And you're kind of curious, hey, how does Hedera fit into all of this? Well, Hedera has the HCS consensus service on Hedera. It's essentially a public and immutable log, messaging log, that when you create a topic, you can then submit messages to it. That's it. It's simply as that. It's powerful because not only does it give you a message log, but it has native performance for about 10,000 TPS. You can amplify your trust with validating data in multi-party databases, notary services, or anything that needs transparency with shared infrastructure. There's guaranteed order. You can get fair total consensus order there with accurate timestamps, a running hash of the topic, and plus a state proof that guarantees correctness. And then obviously we have the ecosystem integrations, things like the Hyperledger Fabric. And at the bottom you see there's a little flow. I think that flow is absolute key to what HCS actually is. You create a topic, you send messages to that topic, those messages get processed with consensus there. And that's exactly what HCS is, and then anyone can audit it, and that's the best part. And I love this quote by Brian Gross from IBM Blockchain, simply putting, Hedera is making a meaningful contribution to furthering the capabilities of distributed networks by exposing this capability. So we'll move forward here to the demo here. So if you guys want to follow along, there's a GitHub repo here for the best workshop, because this is your best workshop for the day. So I'll give you guys a second if you guys want to try that out. And then once we have everyone taking care of that, we'll give it a go. Beautiful. Awesome, thank you so much. And then, so I'll go through the setup and the scripts that you'll go through, and then I'll go through it at the end so you can see what it looks like. But once you get to that repo, you can then clone the repo as you would, cd into the directory, and then run npm install. Then you can just copy the environmental examples and put in your own. And once you have all that taken care of, we can then get your credentials at portal.hedera.com. And if you don't have an account, please make an account, and then you'll show your ID and your key. So the ID you can copy paste over to your env file that you just copied over, and paste it into the 0.0.xx part for your ID, and your operator key will be under more details. So just get that 302 private key, copy that over, and paste it in there. The topic ID will leave blank for now, and then we'll get that in just a moment. And the network should be the test nets as you see there. Beautiful. So the first script we'll run is the create topic. This essentially is creating your own personal topic, your own message. And once it's created, anyone can read this message or any messages on this topic. And then when you submit a message, you are then paying for that message from your account. When this runs successfully, you'll see the output there, as we have there, a green check mark with your ID, the hashscan link. And we'll go through this all in just a moment, but just showing you what it looks like, giving you a little bit of knowledge before you run it so you don't know, so you know what you're doing, you know what you're getting yourself into. The next script is you're going to compute the Merkle root here. By default, this uses a batch of 10, but if you're brave enough on your computer, you can actually update this with a dataset batch -100 or 1,000. You can go more than that, but those we recommend for the first go through of this demo of this tutorial. And then what's happening under the hood, it's first loading that record that we have from the file, and then each record is a payment transaction that has an ID, a timestamp, a type, and a payload, which is all very important. The second step is it canonicalizes each record, and that's just a way of saying that the JSON keys will be laid out deterministically, only because when you have a record, if it's changed around from the record, it'll have a different hash key. So it's all done in the same way, canonicalized, so it always has the same one. So A1 in B2 may not be the same hash as B2 and A1, so it's ordered correctly, so that always happens the same hash. So all these are hashed, obviously, with SHA-256, and then now we're starting to create that leaf, that hash. So you have the Merkle tree being built up from the bottom, then we'll hash those bottom ones together, we'll pair those again, and we'll keep hashing it until we get to that Merkle root. And then you should see that root hash in the terminal as I have down there. It's that 64 hex character. It's about 32 bytes. Whether you have 10 records or 1,000, that root is always going to be the same size, and that's the entire magic that we're going to show off today. So the next one is the third script, which is the anchoring root on HCS. This is where we can now put this on chain. What this script does, it recomputes the root locally on your computer, and that's more of a check for integrity. Then it wraps that into a structured JSON root, as you see there. So you have your schema, your Merkle root, your record count, whether it's 10 or 100, using the hash SHA-256, and then it'll also confirm with the batch JSON that you have. And once you have that, you'll get a transaction ID and hashscan link once you run that script. And then we'll show what that looks like in just a moment. And then there you should have a 260-ish byte message representing all of the proof of all those 10 records, 100 records, whatever it may be, or 1,000, or even 100,000. And all that is cost of less than a tenth of a cent. Now that it's on chain and now it's timestamped with consensus time, it can never be changed, and it's there for the world to see. So that's exactly what we're trying to go for. And when you do this, before going to the next step, you want to maybe wait 5-10 seconds so the mirror node can then take in that information and index that message. So the next two scripts are going to be verifying the batch and then verifying a single record. So the first one is verifying the batch. So you'll run this script for verify batch.js. And what's happening here is that it's recomputing the Merkle root locally with that JSON file. Kind of the same pipeline as before. We have the canonicalization of it, the hashing, and the building of the tree. and then is now querying the mirror node, which is a free public API. There's no auth required, there's no smart contracts, there's no tokens needed, and it's all fetching the latest message from the topic that you've submitted to the HCS. It parses that anchor message, and then what it does is it's pulling the Merkle root that's stored on chain, and now this is the cool part, it's comparing the local root that you have on your computer versus that on-chain root. And once you get that, you'll have at the bottom right, you have a green check mark passing that, yes, these two are working together, there's the same thing. And the best part about this is that anyone can verify this, anyone, anywhere. The mirror node is free and public. You don't need to trust the person who did this. You don't need to trust the special. You don't need to get special keys. You don't need any special permission. The Hedera network is that source of truth. And the part that might be crazy is that if any one particular batch has been tampered with, one byte, this checkmark will not be there. So you know something has been tampered with, something is going wrong. And I think that is the most key part of this whole situation here. And then going back to our airplane example, right? This is how we can prove that that door isn't from an eBay listing, but actually from a manufacturing firm. So you check that serial number on that door against the Merkle root here on HCS, and if it matches, it's real. If it does not match, something's been tampered with, and you can then check without going to find the manufacturer. You can understand what's happening here, and Hedera offers this service to you for free. And then last thing we'll do here is we can kind of check on one single record here. So you can run the script, and it's defaultly going to batch 10 in the 5th record of this 10 record. Maybe you don't want to download all 10 records or 1,000 records. So this way you can only just check one record to make sure that you can get to it and check it. Maybe the other records are maybe confidential, so you don't have access to them. So this is helping you get that one record and checking it against on-chain. So here we'll use actually a Merkle proof. And a Merkle proof is just a path of sibling hashes from your leaf up to the root. So for a batch of 10, that's only about 4 hashes. For 100 records, that could be 7 hashes. For 1,000, it's about 10. And so the verification works is that you start with your record's leaf hash. Then for each step in the proof, for all 4, you have a sibling hash in its position, left or right. And if the sibling on the right is yours, you hash that one first, then the sibling. And the opposite, if it's on the left, sibling first, then yourself. So you're always having a pair partner here to route all the way to what is anchored on HCS. If you have a scavenger hunt, feel free to add that in now. Beautiful. And so what we'll do is I will showcase the code real quick and show you how that works. So just give me just a quick second. So yes, so here now I have the first record. What I did was I've already added this topic to my env file. Let me make this a bit bigger. That could be better. So I've done the first one, as you can see, and it gave me a topic, which I've added to my ID. We'll then run the second compute route. I have it as batch 100. So as you can see, it's loaded 1,000 records. It's canonicalized and computes those leaf hashes, and now I have this root that has my entire records all in one place. Then we'll go and do the third one, which is the submitting the anchor. And once this is built, you can kind of see here that I'll get the hashscan link, so we can kind of go that right now. And it looks just like this. And I can go to messages, and I can see that my message is now here on HCS. Beautiful. And then we'll verify the batch together as well. And you can see both that the mirror node that I have is matching my local data set. My ID is confirmed there as well. And then I'm interested in just doing one batch for a single record. This one's saying data 10, but I think that's okay. I think it's just because it's defaulted that way. But even if that's the case, it's still checking that the root locally for that one single hash is now matched to the one on chain. So just to kind of go back to what we were talking about, just 1 second. So we've kind of learned 5 things here. That the first is the cost problem. When you're trying to store individual records on chain, it does not scale. So we want to get 100,000 messages on HCS without batching would cost $80. With batching, less than 1/10 of a cent. To do this, we'll use Merkle trees to enable this batch verification. You can kind of hash everything down to a single root, and the proof sizes are growing logarithmically. And then HCS is the perfect anchoring layer. It's public, immutable. It's a message log with consensus timestamps. Low cost, high trust, very ideal here. The fourth one is now you can verify entire batches and single records cryptographically without downloading the entire batch, which is great for storing data and not storing excess data. And fifth thing is that we learned is that the mirror node is free and public, so we can then verify with no keys, no permissions, just having the trust required from the network. So yeah, and then I think we have a little bit more time, so we'll kind of discuss a way to run the network on your own computer. But before we go into that, any questions that we have? Fantastic. So I want to talk about Solo. So this Solo is a wonderful tool. I've been using it. A lot of people have been using it as well. This is a way to kind of test projects without having to get testnet tokens. It's a CLI tool, and so this repo you can get access to. I would suggest you guys going through this in your own time. It takes some time to set up, but it's actually fantastic. It's a CLI tool that can run a consensus node, a mirror node, a JSON RPC relay, all inside a local Kubernetes cluster. It is fantastic. I love messing with it, and people have been getting a lot of fun out of it. And so just a quick idea of how to install it. If you have these requirements, Node.js to 22, Docker desktop, and you have Mac OS, Linux, or Windows, and you have a 12 gigabyte RAM, 6 CPU cores, all that's what you need to kind of get it started running on your laptop or devices. I suggest you try it out. And then the instructions to install it are on the repo, but essentially you're just going to set some you'll set some environmental variables. Once you have that, that'll take the longest time. Once you run it and deploy a network, that could take about 10 to 15 minutes or so. So just be mindful of that. And then you can do a quick prompt to verify the deployment, and it'll probably look something like that on the right side there. So we'll have this out for you guys if you're interested. And then the setup is pretty easy. You can then run this same demo that we saw here, and then just change the network configuration on your ENV to Solo, and then run this same setup, the same 5 scripts, and then you can do this on Solo, and you'll see that you can run the entire network from your own laptop, and I think it's magical. So you can then run these whenever you get a chance, and run those 5 scripts again. And this is a quick recap of what we did today so far. That's a wrap, actually. So thank you all for being here. I appreciate you guys' time. I'll also be around. If you have questions about Solo for HCS, I'll be around, so give me a shout. And thank you for your time, and enjoy the rest of Dev Day.
All right, everyone, we're just going to take a quick 20-minute break. And so we'll be back here, and we'll dive into interledger interoperability. So see you soon after the break.
My heart rages around like an ocean in my head because there are so many things that I left unsaid. I can almost feel you.
Hedera DevDay will resume in 5 minutes. Please take your seats, settle in, and get ready for more building.
Nothing feels the same anymore. I've seen this all before. Why didn't I do more? Now I'm picking up the pieces.
Hedera DevDay is about to resume. Please take your seats.
Problems now they pour out, filling up the room with silence. Can you be my nightlight? And I'll be your superhero. Superhero. Can I be your superhero? I'm sorry if it's taking me a while. I'm trying to figure out who I am. The city lights are keeping me up at night, so I don't even bother going to bed. I'm tired of wasting away my time. I would give up everything to be near you. Oh, I miss the days when you were mine, but I can be your superhero. I know I shouldn't call you at night when I'm here all alone, thinking about the last time I tried to tell you what my feelings were like. I'm usually not the one to try to swallow my pride. Oh my, oh, what you doing to me? Ice cold veins when you cut me deep, I'll bleed out. I feel like I'm losing it.
Please join me in welcoming back to the stage RMC, Hashgraph's Head of Developer Relations, Ed Marquez.
All right, everyone, welcome back from break. We're going to resume with our hands-on workshops, and now we're going to dive into cross-chain development and how Hedera connects into the multi-chain ecosystem. So for that, please join me in welcoming to the stage Michael Garber and Jake Hall.
Thanks, everyone. So out there are thousands of blockchains. We all know that, right? And of those 1,000, maybe 100 of transacting any meaningful value. So in the future, where the world will be tokenized, right now we're sitting at about $2.3 trillion. There is maybe $1.5 quadrillion, $1,500 trillion left to be tokenized. When that is tokenized, all these applications are being done on different chains. So how do we communicate that value without being stuck on our own islands? That's what this talk is about.
Yeah.
Thank you for joining us. My name is Michael Garber, and I'm joined by my colleague Jake Hall, and we're going to talk to you today about cross-chain development using Layer 0 on Hedera.
Yeah, exactly. So sort of a quick breakdown of the agenda. First thing we'll be doubling down into is that problem statement that Michael just explained. Then we're going to be looking at the solution and how it actually works, a bit of the theory. We won't go into too much detail because we also then will go into an actual live demo where we can see that theory in practice. So if there's anyone around here who wants to start building using bridges, we've got all of the repo set up for you. I highly recommend coming over, join over, get your laptop out and sort of get engaged. There'll be about half an hour spent on the actual building process. And then we'll just wrap up with sort of key takeaways.
Yeah, and you should have gotten an email. If you didn't get the email, check your email right now. It should give you the instructions of what you needed to get. You need to get some Ethereum on base and some Hedera testnet, HBAR. Okay, so without any further ado, let's talk about the problem and how blockchains are like islands. So if you've ever been to a foreign country, you know what a nightmare this is. So imagine you're Japanese for a second, and you live in Japan. You have your bank account in Japan, and you go to visit South Sudan because you're interested in there. You want to get a cup of coffee, right? So you're in the cafe, you sit down, you have your cup of coffee, the waitress comes, you want to give her your debit card. Sounds simple, right? No, it's not simple at all. Why? Well, the reason is because the banks have never heard of each other, they speak different languages, and frankly, they don't exactly trust each other. So how do we get around that problem? It's sort of like blockchains are like islands. And it's ironic because we started blockchain with the whole ethos that we were going to tear down these walled gardens. But in the process of making these blockchains, they each have their own currency, their own rules, their own economy, their own receipts, and in a sense, we created bigger walled gardens. There's nothing connecting but them. So in a sense, they're bigger walled gardens and blockchain islands. The tokens are essentially trapped.
Yeah. So I think just to sort of summarize, like it's difficult to spend your Japanese currency, I think it's the Japanese yen, in South Sudan, it's also pretty challenging to leverage HBAR on Hedera with the ecosystem, the DeFi ecosystem on Base, and vice versa. Or you can't very easily buy an NFT on the Hedera ecosystem using Ethereum ETH. So the real question is, how do we connect these islands? How do we improve that liquidity flow and reduce silos which naturally occur, naturally arise out of these fragmentations?
So the solution is connecting the islands with bridges. And in the past, bridges were done with 2 custody contracts, typically. There was a contract on the source chain and a contract on the destination chain. And then there would be an operator in the middle with keys to both of those contracts. And naturally, as a result, billions of dollars has been stolen. But thankfully, new protocols have been developed. And at Hedera, we support all the major ones that haven't lost a single dollar yet. Billions and billions of dollars have been transacted, not a single dollar lost. The way they do verification varies slightly from each other. In layer 0, there is a decentralized verifier network that's witnessing transactions, and then a separate executor that's executing, passing a bytecode to a receive function. On Chainlink, you have an Oracle network with a reputation system. And on Axelar, there is an intermediate chain in between the chains to come to consensus on a message before it gets passed off. But this is a signal that we're sending to the market. We're saying, no matter what chain you're on, a chain of meaningful value that you're on, you can connect to Hedera. In a sense, it's like all roads lead to Hedera. And we're saying, come give us a try. See the power and the speed of Hedera. And when you do, you'll get to see the unique properties like fairness of ordering, which no other chain has. So how does it work? So in these next 3 slides, I'm going to go over a general flow of how message passing works with layer 0. It gets a little bit more involved. And if you want those really nitty-gritty, boring details, come and see me after, and I'll answer all your questions. But for now, this is a high-level overview, and hopefully it will be enough to give you guys the gist of how it works. So how does it work? It starts with having we're going to do OFTs, an omni-fungible token. That requires a contract on a source chain and a destination chain. These are identical contracts. They have the ability to mint and burn. And then there is another supporting contract called an endpoint. There's also another thing that supports the endpoint. We're not going to talk about that. This is an ultralight node. We're just going to imagine that the endpoint is an immutable contract that's set up by layer 0, and it acts like a post office. But what do I mean by that? Well, if a user, let's say, wants to send tokens to themselves, let's say they're sending 10 cheese coin to themselves on Hedera from Base. The user initiates a transaction. They send it to the OFT contract. The OFT burns that supply and then creates a payload. That payload is sent to the endpoint, or like the post office. So imagine that the OFT has created a letter, and the letter cannot be sent without being first put in an envelope and stamped and sent off. So that's what the endpoint contract does. It takes the payload, or this letter, and it packages it up in a way, it's called a packet, and it creates a unique ID and then encodes the whole packet. So now we're off the island. We were on the island, now we're off the island. There is a decentralized verified network that is always listening through a WebSocket to an emit packet event coming from the endpoint. And when it sees that, it attests to seeing it and witnessing it. And it calls verify on the destination chain endpoint. And that creates a registry of a unique ID that's been seen and witnessed. When you set up these OFT contracts, you also wire in a configuration and you say, if 2 of 3 of the deviants witness this, then your executor go ahead and execute the payload. So the executor is also connected to a WebSocket listening to that same event, and it is checking the registry on the endpoint of the destination post office, and it's saying, do I see that unique ID? Has it been witnessed 2 of 3 times? The moment that it sees that it has been, it takes the payload, or the packet, and it sends it to the post office. It calls a function called LZ receive. And in reverse order, the endpoint, or the post office, unpackages that packet and gets the payload. And it sends the payload over to the OFT contract, which decodes it and then mints 2 cheese coin to the user A on Hedera. So the important thing to note here about this is that there's no custody involved. And there's no middleman. Well, you might call the deviant and the executor a middleman. And Clipper is removing all of that, so that's wonderful. But it's all verified by independent networks, and it's executed by smart contracts. And there's no custody contract involved. The contract is what you deployed or what the issuer deployed. And that is a high level. I'll now pass it over to Jake to do a demo for you guys. Hopefully you got a good understanding. Ask me a little bit of questions later. I'm going to go around the room if you guys have any questions to get set up.
And if you are taking part in the scavenger hunt, turn your heads over. We've got the secret code on the screen. I'll leave it on there for a few seconds. But after that, I see there's a few people taking their phones out to jot it down. After that, yeah, let's get into the demo. So the scavenger hunt horizon. And let's take a look at the demo. So hopefully you've all received this email containing the prerequisite setup. I'll also quickly go over it just in case there's people who have missed it. So this is, I'm using the GitHub repository, which you can find over here at the Hedera Dev organization. And it's a repository called Template Hedera LZ app, or LZ app, as we'd call it in the UK. And this is the application that you want to clone. So clone this repo. We'll be going through it. Some of the other prerequisites that you need is you need to have a Hedera portal account. So if you don't already, you can just find that over here. We've got the Hedera portal link. And of course, with it, you can get your ECDSA Hedera wallet. You can just use the top one. And if you've got your own wallet, you can actually use the faucet to just sort of send 100 HBAR into your wallet address. You can do that as well. I'll be using the one that you get from the portal because we get a bit more HBAR. But obviously, you'll need to take that private key. And also, another one of the prerequisite steps is you need to top up that same address, whichever one you're going to be using on the Hedera side. You also need to top that up with Ethereum on Base, which is the destination or source network we're going to be bridging to and from. So I'm going to assume you've done that. We'll get into sort of the actual demo, but the steps, you can sort of find more information over here. And now let's get right into the demo. It's going to be quite straightforward. It's basically going to be compiling the smart contracts, following the README, and then we can see on-chain the actual transfers and the actual activity happening. So the first thing you want to do, can everyone see my screen clearly as well? It's all good for everyone? Should I zoom in a bit more or all good? Okay. So the first thing you want to do is compile the smart contracts. And what that does is you can see in the contract directory over here, we've got a whole load of different contracts. This is the first chapter of the bigger EVM bridging application. We'll just be focusing on the first part, which is doing the process that Michael described earlier, transferring a token which is created both on Base and Hedera, and transferring it from Base over to Hedera, so bringing some liquidity in. All of the contracts are over here. You can see that we're, for example, using the Layer 0 OFT EVM smart contract. That does remind me, actually, before you compile the contracts, make sure you run pm install. which will just make sure you've installed all of the relevant dependencies required to run this. But we've got the myOFT contract over here. We'll be deploying this to both Hedera and to Base. And you'll see it looks pretty similar to a normal fungible token ERC20. It's because it is. It's pretty similar. It's just got its own sort of wrapper around it to make it compliant with the layer 0 standard. But deploy the contracts, compile the contracts, PNPM compile. And then what you need to do is you need to deploy the workers, which are, Michael briefly alluded to this, it's the thing which sort of happens behind the scenes. Reason why you need to deploy these is it just makes it a bit easier for testing on the testnet. In mainnet, you would use the workers and executors that layer 0 provide out of the box. So on a mainnet example, you would not need to do this, but for testnet, it's a bit quicker and easier to just have your own local validator network. And all you need to do for that is just run these deploy scripts over here. So this will take us through a few steps. It will deploy the DVN mock and executor on both of the chains. Just sort of click through enter. So that's deployed it using the RPC relays which have been configured out of the box. And we can see now it's deployed these two types of contracts on Base and also on Hedera. So it's my address, the contract, the account which I've been deploying and paying the gas fee for. It's set over here, and the addresses are over here. You don't really need to worry about these because actually we've got some out of the box, this source code automatically reads from the relevant contracts. You don't need to worry about configuring this yourself. Just deploy it, and then the actual backend inside of our application will read from the right place. I'll pause for a second. Is anyone following along? I think there's a few. Yeah? How's it going? Installing. Okay. Well, I'm happy to pause for a second, just while it's going, and I can just run through what we're going to be doing next before actually doing it, so we can get caught up. But the next steps is going to be, well, we've deployed these sort of simple workers, this middleware which handles the execution and the packet creation. Then what we need to do is we need to actually deploy the fungible token contracts, the OFTs, on both chains. We'd be deploying a fresh contract here and using a mechanism called burn and mint, which is the best practice when it comes to doing bridging. You burn it on one chain and mint it on the other, so you don't need to custody and lock the tokens on another chain, which then puts at a risk of someone coming in and stealing them. Then we'll do some wiring up, and then the actual fun part, transferring the token from Base to Hedera or vice versa. How's the install coming along? Yeah, so for the ENV example, it's super straightforward. Just pass in one private key. Make sure it has testnet HBAR and testnet base Sapoli Ethereum. And you can just use the default JSON RPC relays. Hey, man. Sorry, say it again. What does step 3? Why? Okay, good question. Yeah. So somebody just asked, what does step 3 do? Why are the OFT for the simple workers? Basically, what this does is it essentially tells these executors over here, because we've just deployed them fresh, they don't have any context. We've just given them, this is sort of the scaffold for the interoperability to work. We need to let them know which token is going to be which token is it going to be transferring. So this is basically a config file. We can take a quick look at it over here. Asset OFT. Essentially, we pass in, okay, what are the chains that we're going to be working with? What's the ID for the chains? Because each and each chain has its own sort of ID within the layer 0 context. We're just letting the executors know you're going to be working with Hedera and Base, and this is the contract that you're going to be working with. And you can see over here, actually, this is where I think if we go to that, we've got a, it's like this is fetching all of the metadata. For example, what is the metadata for the Base network? What's the metadata for Hedera? Handling all of that. Now, I don't think this is actually necessary when you're using the, if you're using an already deployed DVN or executor. So to my understanding, I don't think that would be required because the operators, the executors and DVNs that layer 0 set up already have that configuration in place. But because we're just deploying it from scratch, we need to sort of give it that understanding. Does that sound right?
That's right. But in the wiring, you're also setting up the routing as well, so you can know which chains are talking to each other. But as far as mocking out the DVN and the executor, that's the step that he just said that wouldn't need to be taken care of. You can pick your own DVN and you can set your own executor, so you can wire it up. But what happens typically under the hood is the layer 0, the layer 0 team has a DVN network they already have, and they have an executor that they already have, and it defaults to that.
Okay, shall we? Let's deploy the OFTs now, and then as well as deploying the OFTs, I'm going to show you how you can actually verify the smart contracts too. So I'll just copy and paste this bit over here. We'll deploy the OFT of course, on Hedera and on Base on those networks. Just sort of click through Enter, and you actually need to do it once. This network doesn't actually do anything. That network flag doesn't actually do anything. So you can just actually paste in this particular section. You can just paste in this section here. But you can see that we've now deployed these fungible tokens, which are compliant with the omni-chain fungible token standard, the OFT, on both Hedera and on Base. And what we can do on Hedera, if we go to the, Base, Sepolia Base Scan already has quite a strong support for ERC20s, because obviously the Ethereum-based networks, the only way you can create a token is ERC20s. It's pretty much the only fungible token that you can do. So they've got, out of the box, you can see these tokens. On Hedera, because we've got different types of tokens, we have a native token, which is more efficient, but isn't a smart contract in and of itself. What you'd have to do on Hedera is go to that contract address, go over to Hashscan, you can sort of search it in, you can find the contract over here. And what you want to do is you want to verify it. So I've already have verified it. I can deploy it again. If I delete our OFT deployment on Hedera, I can deploy it again, deploy a fresh one, and go through the smart contract verification process. So we see it's now deployed a new one. So we've got this new Hedera testnet ERC20 token, which complies with the OFT standard. And verifying it is very straightforward. You can do it manually via the user interface. This is how we'll do it today. But you can also use Sourcify to have it inside of your hard hat configuration or inside of your Foundry configuration. And all you need to do is make sure you're inside of the repository. You've sort of compiled your contracts. Inside of this artifacts folder, there's another folder called build info. And that contains the information of the compiled contracts. You just basically need to upload that file. In there, there'll be some information about the contracts that you've deployed. And via the user interface, it will verify it, and it will be able to realize, okay, this metadata, this build information maps on to the contract that I've just deployed. And once you do that, we'll see that we get an enriched view of the smart contract information. I think because we've compiled quite a lot of contracts,
which we're not necessarily using today, it will take a bit longer than usual. But you can see that's because we've got all of these other contracts over here, Vault Composer, Share OFT, which we're not using right now. If we do have more time, then we can definitely go on to continue with the demo. How's it going for those following along? Michael, do you want to see if maybe, yeah. There we go. Boom. Verify. So it's got the name of the contract. We'll now actually be able to see the ABI, so all of the functions and sort of methods associated with the contract, and the source code for it too. And when we start triggering some events, we'll be able to see it what's the word? Not decrypted, but decoded. We'll be able to see the actual names of the events and the arguments that are being passed in. So let's just take a quick recap as to sort of where we've got to now. So we have we've compiled all the smart contracts. We've deployed the local DVN and executors. We have deployed the OFTs both on Hedera and on base Sepolia. We'll configure the OFT simple workers now. And this is doing exactly what Michael mentioned earlier. This is basically telling the contracts that we've deployed which networks you'll be communicating to and from. And then we can get to the fun part, which is actually transferring those tokens from base over to Hedera. And we'll go into what all of these flags are, this source EID, the destination EID or the endpoint ID, and the other bits and bobs. But sort of in the meantime, while we're setting up the layer 0 asset configuration, what we can do is we can take a look actually at the contracts we've deployed. So we've got a contract, OFT contract on base, which we can see over here. Let's copy that address. We'll be able to see on base that the contract that we have over here has 99,999 total supply. And that's because I did a test earlier on. The Hedera contract, which we just deployed, we can see actually the total supply or the balance of my address. So we can have a look at the address which we're using, which is this address over here. And we can call the balance of function to check how much balance does my wallet have. And as we can see, it's got, this is 100,000 times by 10 to the power of 18. Remember with the EVM, it can't handle decimals. So what you do is you sort of shift it up a bit and you specify how many decimals a token has. In this case, the token has 18 decimals. So sort of 18 of these zeros would be representing an actual decimal essentially. And we only have 10,000 or 100,000 over here. Okay, so we've wired it up. We should now be good to run the transfer part of the demo, which is going to be going through that flow which Michael described earlier, sending a message on base, burning the token so that we don't have this sort of inflated supply, burning the token on the source chain, creating the packet, which says, okay, I've just burnt it over here, let's mint it on this Hedera chain, creating the packet, sending it to the post office, the executor, the endpoint, stamping it, doing all of the checks and balances, and then putting that over to Hedera to then sort of validate it and then mint the tokens and release it to the actual end user. So if we go for the PIM hard hat, LZ OFT send, we can see that we've passed in this source endpoint ID, we've passed in a destination endpoint ID. What this is the ID which layer 0 has for the relevant chains. So base has an ID of 40,000 or 40245. Hedera has an ID of 40285. We're going to be transferring one of those tokens, two, and we'll just be transferring it to the same address. But of course here, this one is actually 1 times by 10 to the power of 18 because we're including the decimals. So the source code will handle that automatically. But if I click enter here, I'm hoping it works. I've just realized it might not because I deployed a new contract on Hedera and I didn't deploy a new one on base, but maybe the wiring would have sorted it out. So we can see it's going through it. The DVN's verifying the message. So the first step was discovering all of the mappings. This is what our configuration did. It's configured, okay, we can actually go from Hedera to Sepolia and vice versa. It is sending the transaction, so it sent 1 tokens, verifying it, and then actually it's executed it. So cool, it's done it successfully. So in theory, if we now go back to our block explorer, if I refresh this, we can see that it's 99998, whereas before there was 99,999. And if we go over to our balance of on our current account, we should see, there we go. We've transferred 1. So this is the 18 zeros, and we now have 10,001 on Hedera. So we've successfully gone from base over to Hedera pretty quickly, very securely. And of course, the use cases here is it's more so than just transferring from A to B, right? What you could do, and actually what I'd recommend if you sort of followed along clearly over here, you can start maybe doing some more complex DeFi flows. So for example, you could set up a vault on Hedera, which maybe is, you can think of it as like an ETF of HTS tokens. And you can set up this bridge such that you pay with Ethereum, ETH on Ethereum, transfer that over via layer 0 to Hedera, then becomes wrapped ETH, and then you can use that wrapped ETH to buy this, invest in this vault. And that vault might then, on the back end, go to SaucerSwap and buy a basket of different HTS tokens. So you've basically given access to users on Ethereum using ETH. You've given them access to exposure to some HTS tokens on Hedera. And that's just really scratching the surface. But yeah, if you want to sort of, I'd recommend doing this in your own time. We've got 2 more chapters as part of this demo where you can actually set up a vault, the ERC 4262, I believe it is. ERC, where are the contracts at? Yeah, ERC 4626. This is the Ethereum standard for doing vaults. You can deploy a vault. You can integrate vaults with layer 0, do cross-chain bridging with layer 0, and then you can sort of extend it even more. So maybe that vault calls some complex logic to provide something like an ETF. How's everyone getting along with the demo? How's it going? So you don't send, you send the, the tokens which you've created on Sepolia. So what you've done, so did you deploy the OFT over here? Did you do this step? Okay. On Sepolia. Okay. Give me, let's get your address. I can transfer you some. What's the Hedera testnet ID? Do you want to share? I can send over some base Sepolia. It's good? Ah. Okay. Okay, cool. So then probably go to the faucet and just paste in your EVM address for Sepolia, and then get some HBAR on that, and then boom. Yeah. So essentially that first step would be deploying the OFT, which again, if we look at the OFT contract, just looks like this, right? Looks very similar to a fungible token. We're specifying that, okay, we're going to mint 10,000 with 18 decimals on both chains. So both chains will start off with 10,000 tokens. Both chains will start with 10,000 tokens on either side. And because we can't inflate the supply over here, there's no mint function. We can't mint more. That's going to be the total supply forever. There's only ever going to be 20,000 tokens in circulation. Of course, once we start transferring tokens over from Ethereum to Base or from Base to Hedera and vice versa, those tokens might be distributed across the two chains differently. Sometimes it might be 5,000 on Base and 15,000 on Hedera. And that's because of that burning mechanism. Whenever we want to transfer it, we don't lock it and mint new supply. We burn it and mint new supply. Should we go over to the wrap-up while we're doing stuff in the key takeaways? Yeah, let's go to the key takeaways, and then we'll check back in. Is things going a bit more smoothly now? Okay. Let's get this done. For us, I want to have one person doing it. This is a success for me. How about, do you want to come up on stage and plug it in, and then we can do debugging live? I think that would be really valuable to those tuning in online. Because often, the problems will be reproducible.
I'm sure it's a step I missed. I just sent the HBAR to that Sepolia account.
Okay, so we've got, do we have a USB-C to HDMI adapter by any chance? Hashgraph Hustlers Live, that's it. It's an hour, we've got an hour here, don't we? We've got 20 more minutes? Let's do it. Let's debug live. This is the real helpful part.
Got like 4 minutes, right?
Just, this is not a mainnet private key, yeah? This is only on testnet. Good.
Okay. Yeah, I think it's the issue where he's not using the same private key for both networks.
100 each bar.
Okay, perfect. Yeah. Perfect. All right, let's go. Let's take it step by step. We'll go right from the top. Boom. So this private key is now lost.
Yes.
So I've lost thousands of private keys. Okay, so are we able to see this screen on the? Yeah, it looks like we're hooked up correctly. That's good.
Right.
So where have you got up to as of now? Let's just go.
So the package is installed. ENV is set up.
Yeah.
Probably showed that already. And that's it. I deployed the contracts.
So where did that private key? Where did you get it from?
From Portal.
From the portal. Okay. So
you need base on that.
Yeah.
Go and do some with
so if we.
But probably what would be better is to just use your private key from Base. And then fund a Hedera wallet at that same address.
Yeah. Or did you have set up Base with MetaMask?
Yeah, I have Base.
Okay, let's get the Base Sepolia account up. That's the one, yeah?
Yep.
Awesome, okay, and you've got home, so we've got testnet ETH. Okay, so let's just go over here, boom, copy that, and then just transfer over some Base over here. Let's do max, and then just keep a bit for gas. View, send that on the Sepolia network. Is this Base or is this Ethereum?
I might not be in the Base.
I think this is actually Ethereum.
Oh, that's why. So I have to roll that Sepolia into
Okay.
Base.
Or what we could do, we could add Ethereum as a network. Yeah. Oh, you could add Base as a network. Yeah. But then we'll get some new stuff. So if we
Get
do
Ethereum on Base.
I might have test on Base. I'm not sure.
do you know cancel testnet mode?
Remember where do you change the network?
So probably settings, networks, Base Sepolia. Let's hook up Base Sepolia. So it's enabled. So I guess if we do,
I guess I just need
maybe over here, add another wallet, find wallet. Do you know what it is? Yeah. So what did you use for the faucet? Did you use Alchemy or something like that?
Yeah.
Yeah. Okay. Do you mind going to the? Let's go to Alchemy, and then we'll top up with Base Ethereum, and because you've already got an account, it should be. Let's unplug this for the time being.
Yep.
Hopefully we don't get 2FA. Boom. Amazing. Okay, let's plug back in. Okay, here we go. So, we've also got, if we go to the faucet, I think there's a Sepolia, sorry, there's a
You'll want to go
Base
Google. This is a
faucet.
terrible search engine.
I'd be right, I think. Faucet, Alchemy, Base Sepolia. Boom. Let's request our. So we'll do it in this account. EVM address. Let's put that through. Hopefully, I'm sure if you sign in, then they give like a.
Yeah, that's the issue.
Okay, do you know what? I will transfer you. I will transfer it to you. I think that would be quicker. So this is is this the same account? So this is, let's do this. I'm going to transfer it to you because I want to have, this is very important. It's getting people to do it end to end is what it's about. So let me transfer you there. We've got 0.0.4337. 4337 547. Boom. Okay. I should have enough base ETH. Base, yeah, I've got 0.25. Okay, let's send over. I'm feeling generous. You're going to get all of my base. All of my base. You're going to get 0.25 Ethereum on Base Sepolia.
You might need some for gas.
Nah, it's cheap. Super cheap.
Nice.
Oh, I just sent HBAR.
Oh.
Okay. Send that one more time. Send it on base Apolia. Oh, no, I didn't. No, that was just a bug. Okay. So let's now go. Let's check this on base Apolia scan first. So if we go to base Apolia scan. Test, there we go. If I paste in your address, you should have 0.25 ETH, and you shouldn't have that no funds error.
Got it.
Yeah,
Nice.
let's go, let's go.
Great.
Hustlers. Okay, back to cursor.
Now deploy it
up.
Now you just deploy, right?
You've done that, and then did you deploy these yet? I don't think so.
I don't think you deployed them, no.
Okay, boom.
I don't have PNP.
Paste. Okay, so we'll do a, let's go, yeah, npm.
NPX. NPX.
Run.
I think it's NPX
yeah,
hard
that's
hat.
right, yeah, npx hard hat. Npx hard hat.
Oh yeah, we figured that out earlier.
Boom. Yeah, that's a really good point. If you don't have PNPM, it's not the end of the world. You can just do npx. So let's do that. Come on, baby.
Yes.
Let's go. We're in the green. Let's do npx hard hat LZ deploy over here. Same stuff. So yeah, it's already deployed. What hard hat does quite well actually is if you've already deployed it on testnet, it doesn't redeploy, it just uses the same one. Let's deploy the OFTs. This would deploy it both on base and Hedera. Then we'll do the wiring up.
I'm really excited about this.
This will be your first
project.
Yeah.
Yeah.
Well, what's really cool actually is actually, yeah, you can do, well, we on mainnet, we've got the official wrapped ETH as well. So that's
You got
like,
the one that staked ETH?
That's
what we're porting.
okay.
We wanna use stake.
Yeah. Nice. That'd be cool. That'd be cool. Let's go. So yeah, so what you can do as well is because the Hedera Foundation did a really great job of improving the sort of liquidity for Ethereum on Hedera and also Bitcoin on Hedera. So now our ecosystems have the official wrapped ETH, the official wrapped Bitcoin, which we can start integrating into our DeFi flows. Boom, it's going. And then we can do the final step, which will be transferring it. So while this is happening, let's just verify our contract on Hedera. So we can take a look at the deployments, Hedera testnet, myOFT. This gives us the address. We can then go over to Hashscan, which I think you have open over here. And we can deploy that.
We don't really need to do the verify step, right?
Well, it does help actually to see, because then we can query the balance on the, HBAR side. I'll do it unplug it just in case you've got any private files. Yeah, just in case you've got any files that you don't want people to see. Do you mind finding the folder for which we were just working in now? That's the one, yeah. Here we go. Let's plug it back in just so we can see. There we go. So here we've got in the, where is it? It's in, was it artifact? Yeah, artifacts, build info. This is the one that we want to give. That's the one. So this will sort of upload it. And probably by now, we've deployed over here. So we can then do the final step, the actual transferring it from base over to Hedera. The to address is to yourself. So that's this EVM address. Boom. You want to specify to use the simple workers. And Let's see it go.
So on the Hedera side, it's associating my EVM already.
We're not using HTS tokens. It's pure ERC for this example.
I'm just trying to understand how it knows that.
Yeah. So just so that I don't think the question was picked up on the mic. Really great question. The question was, does Hedera automatically associate the token before transferring over? And obviously the reason why you asked that is because you're very familiar with the native HTS system, where with the HTS, the native Hedera tokens, it worked. We can check it out after this, but I do want to answer this really great question. So with the native Hedera token service, we have this concept called association, which basically means if you want to transfer a token to another person, unless they've associated to that token, they won't be able to receive it, unless they have auto associations as whatever. But generally speaking, that receiver needs to have said, yeah, I'm happy to take this token. And the reason for that is it's actually a lot to do with compliance. I mean, imagine, let's say you're a business and you've suddenly been transferred a token to your wallet, which is worth 100 grand. Obviously, it wouldn't happen, but it might, right? Suddenly, your accountant's like, hang on, we've just been sent this and we need to pay taxes on that. By saying no, only if I let you receive tokens, only if I associate to it will I receive it. It eliminates all of that overhead. But the reason why it's not particularly important within this context is because we've done a OFT using the ERC20 standard. Yes. So ERC20 is the token standard on Ethereum, which is a smart contract, and there's no concept of association over there. Obviously, with Hedera being EVM compatible, you can use those standards really well. It's super easy to do. However, if you are interested in using the hybrid approach, where you use OFTs and the EVM and the native tokens, what you want to do is you want to have a look at the Hedera docs. Because we've got what's called the HTS connector.
It's a connector contract. I can talk about it.
Go.
It's essentially the OFT standard contract, except it just calls on the HTS libraries for mint and burn.
This is what you want to use.
It is.
Yeah.
But otherwise, it's pretty much exactly the same.
So you can see it's like sort of pretty much the same. We've got this.
It adds in associate in the constructor when you deploy it.
So I think we can see the source code for it. Let's take a look at the OFT adapter. HTS connector contract. So we can see here, for example, this is the source code for it. Example HTS. You can see here that it's using the HTS connector, which comes from over here. And what this is using, it's using the HTS precompose, which if you're a Hedera native builder, you'll be very familiar with. But this is broadly doing the same thing. It's sort of creating a fungible token, which is Hedera's native version of an ERC20. And then it's also, when it comes to debiting and crediting, so it implements the same interfaces, but we're using the Hedera token service burn and transfer. So it's sort of, this is if you want to use that hybrid approach, we'd recommend using this. But we've not done it in this example. We kept it a bit simpler. Yep. This would need things like association for sure. So now, if we take a look at our contract that we deployed on Base, which we transferred it from, if we go over to Base Sepolia, we paste in that contract address, and we click Enter, and we see the OFT tracker. We see that, that started off at 100,000. Now we have 99999. And equally, on the Hedera side, if we go to our, if we do the balance of, let's refresh that. Should now have the ABI. Yep. So if we go to the balance of this address, which started with 10,000 and then received 1, we should see that. Boom. Got that 1 over here.
Awesome.
Let's go, my man.
Awesome.
You did it.
Yeah, cool. Good job.
And that's it. That's how you bridge from Ethereum Base to Hedera.
You want to do key takeaways?
Let's do key takeaways really quickly,
All right. Not quite. There's still some key takeaways. So that was the demo. to get into key takeaways, and we'll wrap it up, and then we're done. So we started out by describing blockchains like islands and how bridges let them talk to each other. And then I described at a high level the technical flow of how layer 0 passes a message from one chain to Hedera, in this case Base. And Jake demoed it and even debugged and helped this guy in the audience to transfer a token.
I gave him 0.25 base ETH in the process.
And he gave him...
Can I send that back, mate?
Yeah. From Base to Hedera.
It was testnet.
So that is our presentation. We hope you guys enjoyed it. And if you have any more questions about, at a deeper level, how the protocol works, come talk to me or Jake, and we'll get you cleared up and send you on your merry way. Thanks.
Thanks to everyone.
All right, everyone, what a great workshop by Jake and Michael on cross-chain interoperability. Now for our last workshop and last hands-on session for the day, we're going to get into a workshop that covers zero-knowledge proofs, confidential execution, and privacy. And so for this workshop, I want to welcome Nadine Lopfe and Keith Cole to the stage.
All right, thank you. Welcome. Hello, DevDay. We are the last workshop of the day, but we, of course, the last is always the best. I would also make a call out that after this presentation, we will be having closing remarks from Richard Bair, and I believe we're also having the winner of the scavenger hunt. So please don't take off after this presentation. Stick around for the closing remarks, and hopefully one of you will be a winner. So the last workshop we have for today is all about confidentiality by design. Basically talking about privacy on L1. Maybe to kind of intro this, I think that for many of us who've worked on blockchain, one of the key aspects of blockchain is that it is public, it's trustless, it's auditable, everything, you can see all the different transactions around accounts. And obviously, this new dynamic of privacy is in many ways very counter to that. But, it certainly is a growing need we see, and we see lots of L1s and functionality around blockchains coming up around privacy, because I think we've all recognized that this is a strong and growing need for users of the blockchain. So just a quick agenda. We'll be first talking about what do we mean by privacy. This presentation is be focusing specifically on enterprise privacy, and I'll talk about that. Some different overview of privacy approaches, and then Nadine will be taking over with the hands-on approach for this, with a hands-on workshop of how you can bring privacy to Hedera for your own enterprise applications. So I'd like to start by, I think when we say privacy, many people think of different things. And in fact, if you look at different technologies on blockchains, many of them take different technical approaches about how they approach privacy. So I think it's always good to first ground with what do we mean by privacy? Now, the first thing we could talk about is, I actually come from the decentralized identity space, is identity privacy. I don't want anyone to know that an account belongs to me. My account on Hedera belongs to Keith Cole. I don't want an association between my account ID or my public key and me as a person. So obviously that's one very important. That's one thing when people think of privacy. That's what they're talking about. Another one, especially as we look towards maybe enterprises or users, is transaction privacy. They don't want to know, I send money to Nadine. They don't want people to know that either my account or her account, they don't want anyone seeing what account did what with what, or what account interacted with a smart contract. They want that all to be hidden. Some other ones, they just maybe look at more amount or value privacy. They're okay with knowing that my account transacted with Nadine's account, but they don't want anyone to know how much or what token. They want all that to be blurred about what was the actual transaction between us. And then finally, I think a growing area is state and data privacy. Often this means not wanting people to know the state of your smart contract. So maybe you could kind of like re-engineer about what was happening with the smart contract. But on Hedera, it can mean things like, you don't want people to see, we have the Hedera consensus service. You don't want people to see whatever you're doing on Hedera consensus service. Or there's many different elements of that. You want to blur whatever state you have on the blockchain. So, there's maybe many more we can add to this, but I think this is a kind of a broad overview of like, what do we mean when we say privacy? Also, the key thing is, a lot of people, when they talk about privacy, they're talking about user privacy. I don't want the government knowing what I am doing on the blockchain or other people. It's what I do on the blockchain is my business. So I think that's certainly one component. Now, we're not going to be covering that much in this presentation today, but obviously that's very important for a lot of people. We're going to be focusing more on enterprise privacy. And I think that there are some very clear, distinct needs around enterprises for privacy. And this is really about that I, as a business, want to use the blockchain. I want all the inherent benefits of the blockchain, but yet I don't want all my competitors knowing like everything I am transacting on the blockchain. Whether you're doing like some sort of a supply management or you're doing stable coins, like I want to hide this from public view so I can interact on the blockchain, but yet not let the world know what exactly I'm doing. So with that focus on enterprise privacy, then we can start breaking it down. Even under enterprise privacy, there's many different characteristics. I think one that many people forget about is that where I think enterprise privacy differs a little bit from personal privacy is that personal privacy, I transaction with Nadine, that's it. I don't want anyone to ever know about it. It's done. I think enterprises are a little bit different in that, especially if you're talking about enterprises doing legit business, they do have this auditability component. Yes, I as a business, my business wants to interact with Nadine's business, but if the government or other parties ever come down the line, I do need like an auditability layer so they can say, yes, like I did send X to Nadine, like that is provable in some later audit situations. And that's a very, I think, core and distinct requirement for enterprises that's also kind of difficult to manage as well. Of course, you have the confidentiality and data protection. I don't want I don't want my competitors knowing who I'm transacting with and what I am transacting. And I also don't want my competitors to know the state of my account, for lack of a better word. Often, like when you're talking about privacy on enterprise, often this is like kind of a consortium situation. So, they want to know who it is I'm interacting with. They want to know the identity of the different parties that they're interacting with. They like a KYB layer. They don't want to be interacting with just anonymous parties because, again, they have a responsibility to know who I'm interacting with. Is that person approved? So you have that whole kind of identity layer with enterprise. Governance and policy. So often, again, these are constructs where maybe you want that governance. So again, back to the identity side, I want to be able to say, like, I have a governance layer saying, like, who are the parties allowed to participate in this private network, and what are the governance and rules around that. And also tying to that is, if I'm transacting with Nadine, and then there's a dispute about what happened, or did I really send her 100 tokens, and maybe she says I sent her 95 tokens, well, then you kind of tying back into the auditability, you need mechanisms in place where you could, if I sue Nadine, there's a way to resolve disputes. Again, that requires that in the privacy component that there is this kind of auditability layer so we can, bring this up in court or resolve a dispute amongst ourselves. And finally, when we're talking about an enterprise system, they want resilience, they want scalability. So, it has to be a robust architecture, especially since, one of the things about privacy, especially if we're going to talk about ZKPs or ZK snarks, this is ever evolving tech. I mean, this tech is rapidly evolving. So I want to make sure I have an architecture in place that's kind of, well, I don't know about future-proof, but certainly it's not going to it's scalable and can move forward without causing too much disruption if the technology underneath the hood changes. So I'll just talk a little bit now about different kind of approaches that the market has taken. Now, some of these are more on the user side, some of these on the enterprise side, and you could probably nitpick about, especially with some of my examples, maybe they don't fit cleanly into these buckets, but I've tried to do the best job I can. So if you take different approaches for privacy, you can start with obfuscation mixing. I think the famous example of that is Tornado Mixer. Basically, you dump a bunch of transactions into a pot, you stir it around, you try to break the unlinkability between transactions. and then you get an output at some later stage, and hopefully nobody can figure out like what A gave to B. I mean, that's the old school way of doing it. It's more statistical than like having cryptographic certainty. But this was certainly an older way. I would say more a legacy way of doing it. Of course, the new way to do it that's all really hot right now is ZK snarks, cryptographic privacy, where you can, basically using data sets, you can prove something about a transaction without actually revealing the data values themselves. And this is obviously like very much in vogue right now, and is probably the leading edge of tech when people are looking to implement privacy solutions, is around using some form of zero knowledge proof solution. And we have our expert kind of sitting here, Rohit, to keep us honest, and he is our in-house expert on all the ZK snark technologies. You have confidential transactions like Liquid Network or Grin, where really their main focus is not so much about maybe shielding the sender or receiver. They're more just about shielding the transaction values. So it's more like a limited utility for privacy. Something you see really new right now, especially like the Oasis network, is around this trusted execution environment where I can deploy an encrypted smart contract on any network, but then you use this kind of trusted execution layer to actually do the operations of the smart contract. So there's quite a few different examples of that out there right now, but it does require like dedicated hardware or trusted execution environment to execute specifically smart contracts or in the EVM layer. Again, maybe more old school, you had like the permission layers. I think the most famous one of this would be like Corda. Corda always talked about transaction privacy, and this was really because they had a permissioned network where they didn't allow people to have visibility on what was happening. Fabric has also kind of gone at that as well, and Quorum. These are like permission networks where the privacy comes from that they only allow some people to see the actual network itself. And then finally, I think probably like, if you look at real life solutions, especially the leading ones, they combine different elements of what I just talked about. They combine ZKP with maybe permission, and you see lots of examples of this. Most recent one would be Jolt ZK EVM, where they've taken a more of a hybrid approach for how they approach their privacy solution. And the other one we'll be talking about Nadine will be presenting is Nightfall, which is again combines different elements off-chain and on-chain for a privacy solution. So what does privacy look like on Hedera? Well, I think it's, we are still looking at the market and the best way to bring privacy for our enterprise users, but certainly something that users can do today. We have HashSphere, and we have a lot of reps here, so this would be the approach that you could have a private network with your partners interacting with it. That's one way to achieve privacy, and that's a very exciting product that we are developing. There's lots of different smart contract solutions out there where you can bring privacy to Hedera, and that's the demo we'll soon be giving, is how you could use Nightfall as one example of how you could bring privacy, very quickly, have a privacy solution on Hedera. And then there's also hybrid, where you can combine something like spheres plus a smart contract solution for a really custom-tailored solution, where you could have a private network with lots of different players, but even within that private network, you can shield interactions from one player to another from other players on that private network. So with that, I'm going to pass it over to Nadine to talk more about what one of these smart contract implementations on Hedera could look like, so you can have privacy for your enterprise.
Awesome. Thanks, Keith. Hi. I'm going to talk to you about Nightfall, and I want to keep this super relaxed because, let's be honest, ZKP can be a bit scary. It's very mathematical. Sometimes people's eyes glance over, so we hope to make this quite interactive and easy to follow. So why Nightfall? Nightfall, as Keith already said, is a really good example of an enterprise solution actually for ZKP. It has actually been developed by Ernst & Young, and Ernst & Young have done this actually on Polygon. So Nightfall enables secure and private transfers, and it does this with ERC20, so fungible tokens, ERC721, so your non-fungible tokens, as well as ERC1155s, so both combined kind of. And it does it with zero knowledge proof and then added scalability through optimistic rollups. Now, with this solution of Nightfall, you can hide who is sending and receiving tokens, how much is being transferred, and also what tokens are being moved exactly. And these are really important things for enterprise clients. Now, what's also really important for enterprises is that while the actual transaction should be confidential, we don't want it to be fully anonymous. And this is where the X509 certificates are coming in. So you need to do some authorization with that. So basically, it's known what identity is on the network, same as, for example, Corda, on what Keith touched on. Now, you can use your own certificate of authority, so it's not prescriptive of which one you should use. So you're kind of free to choose. So benefits, as we already said, private transfers, which everyone wants, and then up to 90% lowered gas fees. Now, it's important to know that, of course, as this has been done with Polygon, and this is 90% lower gas fees to classic EVM tokens. On Hedera, this would have been like less anyways. And then also when it comes to the security, we keep the same ABFT security that Hedera already provides. So it's not making it more secure, it's not making it less secure. Perfect use case. So let's briefly talk about the main elements of this solution. Of course, we have layer 1, which is Hedera. And then here as a layer 2, we have the Nightfall layer, which again is our encrypted private layer on top. So in a nutshell, how the solution is working is that we move our tokens from L1, so from Hedera, into L2, so kind of in a private shielded pool. And then everything that is happening on L2 is going to be fully private. So I can transfer with Keith, I can transfer with Alice, Bob, whoever, and that will not be visible. However, when it becomes visible again to the L1 ledger is when I withdraw. So as soon as I move my tokens back from L1 to L2, I will be going public. I hope that this concept makes sense. Now, how this is exactly working is that we have encrypted commitments. Now, these encrypted commitments, just to go back to, for example, the Corda analogy that we had before, where you have like states that you can mark as historic. It's taking your transaction and brings them together in a basket, and it says as soon as they are spent, it nullifies them and shows that this has been spent and cannot be used again. Same as kind of Bitcoin's UTXO model, if that makes more sense. Also, what we have is roll-up batches. So we will have this group of commitments with the transactions, and then we roll them up into batches to then submit them. So this is the solution in a very high overview. Next, we can look into who's actually the key player, who is on the network, and who is part of it. One part is, of course, the user. The user wants to make a private transfer. Then what we also have are the proposers. So the proposers batch the transactions into blocks, and then we do have challengers. So proposers batch the transactions, and they do that in a kind of optimistic way. So what they're saying is, until no one challenges me that something is wrong with this block or this transaction, we are going to commit that actually to the ledger. That's the reason why challengers come in. They will verify that really everything's okay, and if they flag a commitment or a transaction to the proposer as being wrong, the proposer loses their stake. So it actually makes the whole solution more secure because it's incentivized to do the proposers to do their job correctly. And then last but not least, we have liquidity providers. Now, in this solution, Nightfall, how it is working is that if you want to withdraw, you have to wait 7 days until you actually can get your money back from the smart contract. Why is that? Because of the challenge period. So that challenging period where the challengers can come in and actually say, hey, something's going wrong. Not everyone wants to wait for 7 days. Depends what you want to have to do with the money, but there is where the liquidity providers step in. The liquidity providers will check if everything's okay. If so, they already pre-fund you the money and then later take your stake. I hope so far so simple. I hope everyone's following. Everything's better though with the graphic. So this is how the solution kind of looks like on a high level. We do have our decentralized app. Now we have a client, so the user, me, later when I use the app, I'm going to interact with the client. And I'm going to do, let's say, a deposit or transact, anything. That is going to be pushed from the client to the optimist. So the client is actually assembling the SECP keys, mostly done by the worker who does the heavy lifting. And then it sends it to the optimist. The optimist is bringing all the transactions together and brings it into a block. And then when that's ready to be committed, the optimist moves it to the proposer, who then sends it to L1, which here is Hedera. And now I need to switch my screens, if I can do that. How am I doing it?
Yep.
Perfect, thank you. So we are now going to go semi-hands-on. Why semi-hands-on? I only have 30 more minutes. And unfortunately, deploying smart contracts, start getting some Docker images and doing all of that shebang will take a bit longer than 30 minutes. So we are going to not do it exactly from scratch, but I talk you through and I show you the solution. And if you can start already deploying your contracts, by the time I'm finished talking, you should be ready to go. You can find me later on the studio station, and then we can go through it together if you have any questions. But for now, I want to say hello to this beautiful repository, which is the Nightfall version 3 repo on Hedera. Now, this repository has been created, unfortunately, not by me. I wish it was me, but it was Giuseppe Bertone, my colleague. He has taken the original solution, and what he has done is he adapted it for Hedera. As, of course, Hedera is EVM, we didn't have to do so many changes, but we still had to kind of fork it, find the right branch, and do it. Now, first, I realized we missed the slide. Can we go back to the other presentation quickly? Or I can do it here, actually, sorry. This is important. If you want to follow along, you can scan this QR code, or you can just go to github.com, Internet of Peers /nightfall_3 workshop, and then we can follow along. Sorry. But yeah, now let's dive in how to do a very easy deployment of the Nightfall instance, and then do a deposit, transfer, and withdrawal flow, and we see how this is working. So going back to this repository. Again, thanks, Giuseppe, for doing this tutorial. So the README is actually really good. If you follow along, you should be able to just copy and paste the commands and to go over there. What you need is $10 worth of HBAR, so you need the Hedera account. And can be ECDSA keys, ED25519, actually doesn't matter, just sign up on the Hedera portal if you haven't yet. You will also need Docker Compose and nodes. I usually use NVM as a version manager because it's just the easiest to switch. And then for the browser extension, you either can use MetaMask, or I would highly recommend you to use RabbitWallet. Now, RabbitWallet just has a better UI, and it's also easier to deal with nonces. So if you want to download that now, it's a brilliant time to do so. You just have to, of course, configure it to point to the Hedera testnet. So chain ID 296, symbol, of course, is HBAR. RPC URL 7546, the usual shebang, and you can also put the block node explorer, which of course is Hashscan. Now, for other suggestions, I usually use Visual Studio Code, also for this demo, just for the overview. You also will need to have jQuery installed if you don't already have. And yeah, that's pretty much it. And we can go into the environment variable setup. So if you see here, you will need your native account ID, you will need your EVM account ID. Now, how I usually like to do it is same as Giuseppe, is to just put it into my shell file. So my here it's set as HRC. Why? So you can just use it across multiple repositories, so you do not have to constantly import it as a new file. However, of course, you can do it just as an end file on project base. Then if you go down, you see here the repositories and the command to actually git clone them. So you have two repositories here. One is Nightfall version 3, and the other one is the workshop. What you have to do is you have to go to the Hedera branch. That's very important, because Nightfall version 3 actually is discontinued in a way. So there's now Nightfall version 4, which is a bit less stable. And we went from the Aquafix Eve Sepolia branch, which is important to go for, because it has a lot of fixes that the main branch doesn't have included. As soon as you have downloaded that repository, now comes the fun part that will take at least 5 minutes, with this internet connection probably 10. And that is, we have to download our Docker images. So as you can see here, we have a client, a deployer, an optimist, the proposer, and it's going just to pull the newest version of the images. And after that, we can move on to the contract deployment. And you see, I'm kind of rushing through the setup steps because really no one wants to see 10 minutes of code in a terminal being deployed. But what I want to point out is these really cool setup scripts that we have here. So if you actually switch to your Nightfall directory, there's a Nightfall _3 workshop directory, which has helper scripts that help you show what your current HBAR balance is without having to log into your wallet, or it also helps you to create a new account. Because for this workshop, we will need 2 accounts. So if you just so far have one, you can just cd into the Nightfall -3 workshop directory, run create account, and what will happen is it gives you a full new EVM address, private key, everything that you need to know. Next, you can just make note of that account and transfer some HBAR into that account, because for the workshop, as we remember, we need $10 in both accounts. If I run the script here, I can see transaction successful. So that means my both accounts now have 100 HBAR, and I can move on. Next step, favorite one ever, JSON RPC relays. We already heard a lot about it today. Why run your own JSON RPC relay? Mostly because of rate limits. If you use Hashio or anything else, you can run into rate limits, and also for logging and debugging. If you use your own JSON RPC relay, you can just click into it, you can see your logs. Your life is so much easier. What you can do, you can check that your environment variables are properly set. So you can cd into Nightfall 3 workshop directory. Again, there's a script for that. And you see everything's properly set. We're ready to go. And then I can run my local JSON RPC relay if I have not already done so. All of this is, of course, also in the README, so it should be pretty easy to follow and self-explanatory. Next step is deploy the contracts. And here again, if you need to check that you have everything environment variable-wise, you can do that. And now in the configurations, we have all already done this for this workshop. So if you clone the repository and follow along, you do not have to worry about configuring your environment variable, your deployment environment variables, because they are already done by us. Of course, if you would want to have it as a productionized solution, you would want to customize these. That's the reason why we flag the files to look into. And then the deployment can happen. If you run the deployer, it should take 10 minutes, maybe 20 here, who knows. And after that, if you go to Docker and volumes, you should see this artifacts and build and proving files directory. Now, you can see here we have the challenges, you have the proposers, the shield contract, which is the most important, and then, of course, the X509 certificates that are in there. Proving file-wise, we have here the powers of Tau. So these are the Romani files. They are coming straight from the Polygon or the Google API store. If you don't trust them, you can create your own ones. It's going to take some time, but I would heavily, heavily recommend just going with the ones that we have in here. And then, next step, very important. In Hedera, of course, we don't really have the concept of a block. So what we want to do here is we want to set the state genesis block, and we want to set it to the current block, because otherwise we're going to go all the way back, and the mirror node doesn't really do anything here that's longer than 7 days. So this is this command here. You can copy it, you can paste it in your terminal, and what you can see here now is it says the current block number, and it will put it for you in your variables file. Again, if you want to look what's in there, you can. They're all in the bin directory. It's all already been pre-configured by us, but you can play around with this. And then when everything is deployed and done, we can remove the orphans, and we can actually start Nightfall, and this is now where it gets fun. So what we're going to do now is we're going to go into the right directory. We have to make sure that we are in Nightfall 3, not the workshop. We want to be in the proper solution. And then we set the version to node version to 18, and we're going to start our Docker containers. And as we can see here, a lot of logs. A lot of logs that are hard to decipher because there's a heartbeat, and I would really recommend to toggle it with just this post request. It's going to make everything a bit more readable. But you know what makes stuff even more readable? Not having it just in one terminal. So the best that we can actually do is open a couple of new terminal ones, and we can do this with these 2 commands here to only get the logs for the client and the logs for the optimist, which are going to be the most important ones for the demo application that we're going to run in a sec. Now you can all see my very beautiful desktop wallpaper. And me shuffling around some terminals. I hope everyone can kind of see that. So it's just important that you kind of can see, spot what's happening there. At the moment in the client, not so much. Of course, in the Optimist also not. But as soon we're up in the UI, we will see how the transaction moves from client to Optimist and then later to Proposer. Awesome. Next step and last step, start the Proposer. And then we can finally start our demo UI. I'm just doing this in my VS Code. There we go. Of course, I could also do this just in my Docker desktop, I would just constantly have to switch the different logs. So if you want to do it and just follow along, I would highly recommend to do it this way as a setup. And we see here the proposer has been registered in the Optimist. So we get a 200 return from the register endpoint. So our setup is fine and ready to go. And we can finally start a demo UI. Why a demo UI? We all love scripts, but it's just so much easier to follow along and to see some concepts, especially when it comes to users in or wallet users in L1 and wallet users in L2. So to do this, you can cd into the Nightfall 3 directory and then into demo-ui. And then we're gonna just switching here profiles because separation of concerns. There we go. And then this is our beautiful demo UI. This is very simple. You can now see my Rebby wallet here on the top, which is the blue bunny, which we're going to look into. And then what we can see here is the wrapped HBAR address. So what we have to deposit actually is wrapped HBAR, not normal HBAR. Now, if you look, I have already set up 2 accounts. One is Dave and one is Carl. And Dave as well as Carl have already wrapped HBARs. If you don't know how to get wrapped HBAR, it's actually super simple. You can just copy that address that you see here on the screen, and you can send the amount of HBARs that you want to have as wrapped HBARs to the contract, and the contract is going to return wrapped HBARs to you. That's this address I'm referring to. So just to show you, I can do 100 HBAR. I've just saved here the contract address. I click send. I sign this transaction, of course. And now I see I have 100 wrapped HBAR more. So more than ready to go. So Carl and Dave are our 2 personas on L1. So they have our private Hedera keys, and we're now using them to follow along. Whoops. Let's go. Now, what I can do, sorry, I went a bit too quickly. Great. So what I can do now is I can select Carl, and I can create a user on L2. Now, I'm going to, just for the sake of making this concept a bit more clear, I'm going to not name this user Carl. I'm going to name this user Alice. And this user is going to get a mnemonic. You can use your own, or you can just check one here in the UI. And then I click Add User, and I see that Alice is now coming up on the right side of my screen. And you can see that Alice has also this green kind of circle dot, which means that Alice is currently active. I see Alice's L1 balance, and I see Alice's L2 balance. That L2 balance is from some tests before that were still hanging around. And if I see here in the client, I can see that I call the endpoints for commitments, for balance, how it hits the client, and how I create Alice. I can fetch balances if it doesn't do it properly for me. And then I will get that back. And then it goes, as you can see here, to the Optimist, who also returns me logs. Now I'm going to do the same thing for Dave. So I'm going to switch to Dave. And now I see Alice is not green anymore because we have that link. And of course, if there would be a productionized setup, we would have a one-to-one mapping, and we wouldn't have both in the same UI. But just for the sake of this workshop, we are doing this. So what we're now doing is we're creating Bob. And we can see that Bob is active on the right side. Again, here on the client, we can see that we have a balance request. And it's really nice to see in the logs how we can follow these transactions. Now, having both of Alice and Bob here as our L2 users, what we have to do is we can deposit some wrapped HBAR that we can actually private transfer with onto the contract. So we are going to do this right now. So I switched back to Alice just because Carl was the first one that I first used. And then I'm going to deposit some wrapped HBAR in the contract. This is 60 wrapped HBAR. This is not some other crazy number. This has 8 zeros because of the decimals that we need. Very important to know. And then I want to talk about that set fee 10. This fee is set by the proposer. The proposer will need that fee. So we always have to think you need to add the fee, or you're going to put like 59.99999 or something. Now I can click deposit, and it wants me to sign the transaction because, of course, we're depositing this into a smart contract. And now I sign, and I can see here on the client already how the transaction hash is coming in. I see the proof, I see the nullifiers, compressed secrets, and I can see the call and a 200 status of the deposit endpoint. It's going to take a while here, but I can see how this has also reached here the optimist. So the transaction handler has received something. And now we can do the same for Dave. This has not reached the proposer yet. This currently is just been doing client to optimist. So if you think I forgot to show the proposer logs, don't worry, we're not that far yet. Same situation here. We're going to put 50 wrapped HBAR. I'm going to add a couple of zeros, and I'm going to add the 10, the fee for the proposer. I'm going to sign this transaction also for my second user, which is Dave. And then again, I see here in the client how it hits there first. It generates the proof, and then it's getting picked up by the optimist. And now we wait, and ta-da. Now I already see people thinking probably, okay, what is now happening with the blocks? We could, of course, make a couple of more transactions to be sure that we create a block. However, we have here this nice cheaty button on the top, which says in nice and green, make block. So we can click that one, and we actually force to produce a new block, which we've been doing just now. So you now see again here we have a commitment here, and then we now see how this is moving. Block proposed is showing up here in the events. This is new, we haven't seen that before. We see the received block numbers, we see the hashes, and then here we see again calling the endpoint for commitments. We go down, and then here in the optimist, we can see it received the block proposed event. So we now have a new block. Oops, being mindful of time, I will have to speed this a bit up. So having the new block now, I can see that my L2 balance has changed. So Alice as well as Bob have new money. Now I can move to the transfer. And for the transfer value, I again can select, where are we? Can select something like 10K, let's say 20 wrapped H bar. And I can see where I'm currently at. I am Dave. And then Dave is sending this to Alice. And I'm set off-chain. Why did I click off-chain here? Really important. Again, everything that's happening on L2 with these two users is fully private. It is not hitting L1. That's the reason why it is fully private. So all these transfers are instant like this. And also when I click transfer, you can again see how it's hitting the client and then the optimist. But as you have seen, it did not ask me to sign in my Rabbi wallet. It did ask me to sign when I deposited, but not now in the contracts. And if I go to my proposer, I see an off-chain transaction call here. I can do this now as many times as I want, and this solution is going to be fully private. Next, let's talk, because I only have a minute left, let's speed up and go to the withdrawals. So if I want to withdraw something, it will, of course, ask me again to sign, because all the withdrawals are going to touch L1. So Rabbi Wallet will come up, Rabbi Wallet will ask me to sign, and again here we can see in the logs, if we follow, how it hits the client, how it hits the optimist, and then the proposer. Now, really important here, the 7 days. We are going to withdraw, and we can see the L2 balance changes, of course, straight away, but the funds are locked in a contract, and they will only be able to be released after 7 days, after the challenge period is complete. So we don't have in this demo challengers, and we also don't have liquidity providers, just for the sake of time and complexity, but they are in the code. So if you want to download the repository, you can try this out as well and also challenge some of these blocks. In this demo, everything was quite easy. Again, just to wrap up, we set Rabbi Wallet up with 2 private keys, so 2 L1 users. Every one of these L1 users was used to create a person on L2. We deposited wrapped HBAR, which we got by sending HBAR to the wrapped HBAR contract to the layer 2. We can do as many transfers as we want on that layer 2. It's going to be private. And the next time when we withdraw, we're going to go back to L1 and we're going to go back to public. I hope this was helpful. I hope that some of you will download the repositories, deploy the contracts, and try a couple of these transfers yourselves. You can also, the contracts are verified also on Hashscan. Unfortunately, I didn't have the time now to show you that. But if you go on Hashscan, you can see the verified contracts. You can see the difference of how a private transaction looks like to a public transaction. If you have any questions, please find me at the studio station later. Talk to me, talk to Keith, or talk to Rohit, who's our CKP expert. Thank you so much.
Yeah, just in conclusion, yeah, thank you to Nadine and Giuseppe for that great demo. Again, this is just to give you an idea. I mean, we're not saying you should use Nightfall, but there's many smart contract solutions out there for privacy. This is just an example of one of them if you're looking to implement privacy, and we hope in the future there'll be many more. The main call to action for you guys, we want to hear what your requirements are for privacy, whether it's enterprise or user. Please come find me and Nadine. We'd love to hear your product requirements as a product guy, and we're looking towards the future of privacy on Hedera. So thank you all for attending.
All right, everybody. Hey, all my friends over in the builder zones. If you guys wouldn't mind, just come up close for a little bit. Yeah, for Mark, all you guys, come up close, all the people who are out there. We are at the conclusion of our Dev Day today in 2026. And I thought that we ought to first, if you wouldn't mind joining me in a round of applause for all the people who put their time and energy into putting this event together. All the wonderful, the food and the planning and the facilities and everything. Thank you very much. Also, for all of those who prepared and presented today, if we could give them a round of applause as well for the effort in trying to make that come together. And thank you for coming and joining us today. Now, if you came to Dev Day and you leave without learning the name of one new person, I am deeply disappointed in you. Oh, hi. So at least meet 3 people, because following this, we have the happy hour. We're going to have socialization opportunity. At least you should meet 3 new people. And if you're on my team, you need to meet at least 10 new people. All right, 10 new people. Just mix it up. Let's get to know each other. Make some new connections. That's the real value of doing these things, is that we have an opportunity to get to know each other in a way that we've never known each other before, or maybe never have known each other at all before. So make sure that you take advantage of this opportunity to do that. I want to thank you for coming, spending the day with us, hopefully learning a little bit about what we're doing and some of the different ways to use the network. And that's it. We'll be back again next year, and I'd like to go ahead and invite Ed up. He's going to do the part that everybody's really here to listen for, which is like all these awesome things that are sitting up here that I really wish I was, able to win. But Ed, I'll swap you.
Thank you, Richard. All right, everyone. Did you enjoy Dev Day today? Woo! All right. So this is the moment that everybody has been waiting for. Now we're going to announce the winners, but before we get to the winners, I do want to remind you to register to HederaCon today. That's going to be in Miami on May 4th, and it's going to be another incredible opportunity with amazing content, amazing panels and talks, so be sure to join that event in Miami. All right, so for the scavenger hunt winners, one requirement is that you have to be here to claim your prize. So if you're not here, we'll just go to the next person who ranked. What are the prizes? As I said, $3,000 worth of prizes. We got Quests or MetaQuest, Mac Mini, PS5, DJI drones, AirPods, Nintendo Switch, and a few more things there. So for our first place winner, this person's going to come to the stage. You're going to select your prize, whatever you prefer there, and then we're going to take a picture, and then you can go to the networking session. All right, so Garrison. Is Garrison here? Woo! First place with 975 points. This man was committed. What are you going to get? All right, so pick your prize. Mac Mini, all right. Good stuff, man.
Thank you so much.
Take a picture. Congratulations, Garrison. Second place for the day, we got Boulder Magic with 960 points, so that was pretty close. Boulder Magic, there he is. We're just gonna have to see some credentials here. All right, so pick your prize. He was going for the Mac Mini, and now he's going for the PS5. Great choice, great choice. Oh, yeah, that's right. Picture. I think he was very excited to go unpack it and start playing right away. But awesome. Congratulations. Third place, we got CryptoGoat. Man, these usernames. CryptoGoat, 960 points. So come to the stage. All right, and he's going for the Nintendo Switch. Congratulations, man. Thank you. Thank you. All right, so now for number 4, we got Mark Kina. Mark Kina, you here? Mark? Hey. Congrats, Mark. That's 915 points. And he's going to go for AirPods. Congrats, man. All right, we're down to our last 2. 5th place, we got Nicholas GV. Nick, all right. Nico, all right. Congratulations for those of you who haven't met Nico. He's one of our ambassadors in Latin America, so congratulations, Nico. And he's going for the MetaQuest. All right. In 6th place, we got Juanma. Juanma here, all right. Congrats, Juanma, woo! And he's going for the one choice he got, which is the drone. Congrats, Juanma. All right, everyone, that's it for the day. I hope you had an amazing Dev Day. I know I did, and I appreciate all the work, all the networking, all the amazing experiences that went on today. So with this, let's close the event, and let's go network. Thank you.
You take the light with you and you go. You're not coming knocking on my door now. I try to lie, was it always so? Cause nothing feels the same anymore. I've seen this all before, why didn't I do more? Now I'm picking up the pieces.